the theory of everything. In physics, we've uncovered fundamental laws and equations that describe the universe with astonishing accuracy. These laws can predict the motion of planets, the behavior of atoms, and even the origins of the cosmos itself. However, each of these laws only applies to a specific part of reality. We currently have one set of equations that explains gravity, Einstein's general relativity, and another that governs the world of subatomic particles, quantum mechanics. The problem is, these two frameworks don't align. They're both incredibly successful in their own domains, but when we try to combine them, such as in extreme environments like the center of a black hole or the instant after the Big Bang, the mathematics breaks down. The theory of everything is the idea that there may be a single, unified framework that can explain all aspects of the universe, every force, every particle, and every interaction. It would seamlessly connect the curvature of space-time with the quantum structure of matter. For decades, physicists have searched for this ultimate theory. Some of the most ambitious efforts include string theory, loop quantum gravity, and grand unified theories. These ideas hold promise, but so far, none have been experimentally confirmed. The mystery persists. Is there a single elegant principle underlying all of nature that we have yet to discover? Or is the universe inherently fragmented, governed by separate rules that refuse to unify? The search for a theory of everything is not just about solving a scientific puzzle. It's about uncovering whether the universe follows a hidden, universal code, or if the final piece of the puzzle simply doesn't exist. The universe's missing antimatter. The universe, as we know it, shouldn't exist. Not the stars, the galaxies, or even people. In the first moments after the Big Bang, both matter and antimatter should have been created in equal amounts. And when matter meets antimatter, they annihilate each other completely, vanishing in a flash of pure energy. It's one of the most fundamental interactions in physics. So if matter and antimatter were created equally, they should have wiped each other out entirely. But that didn't happen. For reasons we still don't fully understand, there was a tiny imbalance, a slight excess of matter. Just one extra particle of matter for every billion pairs of matter and antimatter. That minuscule surplus was enough. When the rest annihilated itself, that tiny fraction of leftover matter remained. And from that sliver came everything. Every star, every planet, every atom in your body. So where did all the antimatter go? Or more precisely, why was there more matter in the first place? This mystery is known as the baryon asymmetry problem, and it cuts to the very core of modern physics. Some experiments have shown that particles and their antiparticles don't behave in exactly symmetrical ways, a phenomenon known as CP violation. But what we've observed so far isn't nearly enough to explain the vast imbalance between matter and antimatter. Some theories suggest that unknown processes during the Big Bang might be responsible. Others point to hidden particles or forces we haven't yet discovered. There's even speculation that an entire antimatter universe might exist, forever separated from ours and unreachable. For now, though, we're left with a paradox. A universe that, by all logic, shouldn't exist, but does. The mystery of the missing antimatter is more than a scientific question. It's a quiet, humbling reminder that everything we are is built on a mystery we've yet to solve. The strange matter contagion hypothesis. In the realm of theoretical physics, there exists a chilling and fascinating idea known as the strange matter contagion hypothesis. While it may sound like the plot of a science fiction movie, the implications of this concept are both serious and potentially terrifying. The hypothesis centers on a mysterious and hypothetical form of matter called strange matter. This substance is believed to be composed of strange quarks, a type of fundamental particle that only appears under extreme conditions, such as those found in the dense cores of neutron stars. Unlike the ordinary matter that makes up everything in our daily lives, strange matter is thought to be more stable than regular matter. In fact, Some scientists propose that it could exist in a form that is not only more stable, but also far more powerful and potentially destructive. The most unsettling part of the hypothesis is the idea of contagion. What if strange matter could somehow infect normal matter? Imagine this. A tiny fragment of strange matter comes into contact with a regular particle. Instead of remaining isolated, it triggers a transformation, turning the ordinary matter into strange matter as well. Like a virus, it could spread, particle by particle, until it transforms everything in its path. The implications are deeply disturbing. If strange matter could propagate in this way without restraint, it might consume all known matter in the universe, planets, stars, even entire galaxies, gradually converting everything into this alien substance. The universe as we know it would be overwritten by a new form of matter governed by unfamiliar physical laws. Despite the fearsome nature of this idea, it has captured the attention of scientists studying the most extreme environments in the cosmos. Could strange matter actually exist? Could it really spread like a cosmic infection? Or is it merely a theoretical curiosity, a dramatic but impossible scenario? The strange matter contagion hypothesis remains one of the most intriguing and disturbing puzzles in modern physics. Whether it proves to be real or not, it challenges our understanding of matter, stability, and the fundamental nature of the universe itself. Anomalous magnetic dipole moments. One of the most fundamental concepts in physics is the magnetic dipole moment, a measure of a particle's magnetic properties. It plays a crucial role in determining how particles like electrons behave in magnetic fields. This moment is closely tied to a particle's spin, allowing it to interact with magnetic fields in predictable ways. But what if this behavior isn't as straightforward as we once believed? What if the magnetic dipole moments of particles like electrons are more unusual, more anomalous, than our current theories can explain? This is the mystery behind anomalous magnetic dipole moments. In the 1940s, scientists began calculating the magnetic dipole moment of the electron using the principles of quantum mechanics. Their predictions matched experimental results quite well, reinforcing confidence in the theory. However, in the 1990s, a more precise measurement revealed something unexpected. The electron's magnetic moment was slightly off from the predicted value. This subtle discrepancy, known as the anomalous magnetic dipole moment, is not simply a measurement error. Instead, it suggests the influence of something unknown affecting the electron's behavior. Some researchers believe this anomaly could be the result of previously undetected particles or even new, undiscovered forces of nature hidden within the quantum realm. Could it be that electrons are interacting with unknown particles or forces that we have yet to observe? As experiments grow more precise, the anomaly persists, deepening the mystery and suggesting that there may be gaps in our current understanding of particle physics. This anomaly might be more than just a small deviation. It could be the first glimpse into a deeper layer of reality, a frontier of physics waiting to be explored. Though the anomalous magnetic dipole moment is one of the tiniest inconsistencies ever detected, it holds the potential to unlock major scientific discoveries. It could even challenge and reshape our fundamental understanding of the forces that govern the universe. It is a puzzle yet to be solved, and as research pushes forward, the answers might rewrite the very foundations of physics. Levitating plasma clouds. Imagine standing in a laboratory, gazing at a strange, glowing cloud of gas suspended in midair. There are no strings, no supports, just a luminous cloud of plasma, hovering in perfect stillness. This captivating sight represents the mystery of levitating plasma clouds, a phenomenon that has puzzled scientists for decades. Plasma, often referred to as the fourth state of matter, is a superheated gas composed of charged particles, electrons and ions, that can conduct electricity. It exists all around us, from neon signs on city streets to the blazing core of the sun. Despite its prevalence, creating and sustaining plasma in a controlled laboratory environment is incredibly challenging, especially when it begins to levitate. Under normal conditions, plasma behaves like any other gas. It expands and dissipates. However, scientists have discovered that, under specific circumstances, plasma can float in place, held aloft by invisible electromagnetic forces. This remarkable effect occurs when strong magnetic fields interact with the plasma's charged particles, trapping them in a stable, suspended state. The real intrigue begins when researchers try to understand how and why these clouds of plasma remain suspended without any visible support. How do these electromagnetic fields manage to keep the plasma from collapsing or drifting away? And what can this teach us about the fundamental forces of nature, particularly in the extreme domain of high-energy physics? Some scientists believe that unraveling the secrets of levitating plasma clouds could lead to revolutionary advances in technology. For instance, this knowledge might pave the way for breakthroughs in fusion energy, offering a new, clean power source. Others speculate that it could play a role in the development of advanced propulsion systems, perhaps even enabling space travel that taps into the forces that govern the universe itself. The phenomenon of levitating plasma clouds challenges many of our assumptions about matter and energy. It serves as a powerful reminder that, even in a world defined by high-tech research and rapid innovation, there are still deep mysteries waiting to be uncovered, mysteries that could reshape our understanding of the cosmos. And at the edges of this discovery lie even stranger questions, such as those posed by anomalous magnetic dipole moments, puzzles in particle physics that hint at new physics beyond what we currently know. Anomalous solar neutrino behavior. The sun is the powerhouse of our solar system, providing the light and energy that sustain life on Earth. However, there is a mysterious and almost eerie aspect of the sun that has puzzled scientists for decades: the behavior of solar neutrinos. Neutrinos are subatomic particles produced in vast quantities during the nuclear reactions occurring in the sun's core. These particles travel through space at incredible speeds and, upon reaching Earth, pass through matter virtually undetected. Because they rarely interact with anything, neutrinos are incredibly difficult to observe. Yet, they carry crucial information about the inner workings of the sun. For years, scientists built highly sensitive detectors to measure the number of solar neutrinos arriving on Earth. According to theoretical predictions, these detectors were expected to register a steady and specific flow of neutrinos. But when the first experiments were conducted, the results were surprising. Only about 1/3 of the predicted neutrinos were detected. This discrepancy became known as the solar neutrino problem, a scientific mystery that baffled researchers for over 4 decades. As scientists delved deeper, they discovered that the missing neutrinos weren't vanishing at all. Instead, they were changing forms. The breakthrough came with the discovery of neutrino oscillations, a phenomenon in which neutrinos switch between different flavors or types as they travel through space. Some of the neutrinos produced in the sun's core were transforming into types that were harder for detectors to pick up, which explained the missing numbers. This discovery was monumental, reshaping our understanding of both neutrinos and the sun's energy production. But it also raised deeper questions. How does this transformation occur? And what does it reveal about the fundamental nature of matter and the forces that govern the universe? The mystery of solar neutrino behavior opened the door to a new realm of physics, proving that even the tiniest particles can carry profound secrets about the universe's inner workings. As we continue to explore these elusive particles, there's no telling what other mysteries we might uncover. Theoretical magnetic monopoles. Imagine a magnet, something simple and familiar, like the kind you might stick to a refrigerator. Every magnet you've ever seen has 2 poles, a north pole and a south pole. But what if you could find a magnet with only one pole, either a north or a south, but not both? This strange and fascinating idea is known as a magnetic monopole. Although it might sound like science fiction, magnetic monopoles have captivated physicists for over a century. In theory, magnetic monopoles are particles that carry a single magnetic charge, either a north or a south pole, but never both. This would defy the basic rule we observe in everyday magnets, where poles always come in pairs. If magnetic monopoles do exist, they could revolutionize our understanding of electromagnetism, one of the four fundamental forces of nature. The idea of monopoles first gained serious attention in the 1930s when physicist Paul Dirac proposed their existence. According to Dirac, if magnetic monopoles were real, they could explain why electric charge is quantized, why it always comes in discrete units rather than a continuous range. In essence, discovering a monopole could unlock deeper insights into the fundamental structure of the universe. Despite decades of experiments and extensive searches, no one has yet discovered a magnetic monopole. This has led to an ongoing debate in the scientific community. Are magnetic monopoles purely theoretical, or could they be hiding somewhere in the universe, waiting to be found? Some physicists speculate that monopoles might exist under extreme or exotic conditions, perhaps in the dense cores of certain stars or created briefly during high-energy particle collisions. Their rarity, or perhaps their elusive nature, may be the reason we haven't observed them yet. The mystery of magnetic monopoles continues to captivate researchers. If discovered, these elusive particles could open the door to new physics and reveal hidden layers of reality. Until then, the search for the magnetic monopole remains one of the greatest unanswered questions in modern science. A cosmic riddle that, if solved, might change everything we know about magnetism and the forces that shape our universe. Quantized inertia theory, a new frontier in physics. Imagine a universe that challenges the very principles of physics we've trusted for centuries. This is the premise behind quantized inertia theory, a bold and mysterious idea that could reveal a hidden layer of reality within the cosmos. The theory was first proposed in 2007 by physicist Mike McCulloch. At its core, quantized inertia, QI, suggests a radical reinterpretation of inertia, the resistance of an object to changes in its motion. In classical physics, inertia is understood to be directly tied to mass. It's a foundational concept in how we understand movement and force. But McCulloch introduced a provocative idea. What if inertia isn't solely dependent on mass? According to quantized inertia, inertia could be influenced by unseen energy fields in space, including vacuum fluctuations and cosmic dark energy, forces typically considered irrelevant in most conventional models. This new perspective opens the door to a range of possibilities. The mystery deepens when this theory is applied to galactic behavior and space travel. McCulloch proposed that objects in space may experience a modified form of inertia, which could help explain long-standing astronomical puzzles, like the rotation curves of galaxies. Galaxies spin in ways that defy predictions made by current gravitational models. This discrepancy has baffled scientists for decades and has largely led to the introduction of dark matter as a placeholder for the unknown. But what if we don't need dark matter to explain these cosmic motions? Quantized inertia might offer an alternative explanation, suggesting that changes in inertia, not hidden matter, are behind these gravitational oddities. Beyond explaining galactic motion, QI also sparks ideas about the future of space travel. If we can understand how inertia behaves on a quantum level, could we engineer new forms of propulsion? Could we tap into the energy woven into the fabric of space itself? The implications are staggering. Efficient spaceflight, energy extraction from the vacuum, or entirely new technologies. Although still controversial and far from mainstream acceptance, quantized inertia poses a profound question. What if the forces that govern the universe are not what we think they are? The mystery of quantized inertia continues to challenge our understanding of space, time, and the very structure of reality. The journey for answers is only beginning. The Transplanckian problem. In the world of physics, there exists a boundary so small, so elusive, that crossing it seems almost impossible. This is the mysterious realm of the Transplanckian, the domain that lies beyond the Planck scale, the smallest meaningful unit of measurement in the universe. At distances shorter than a trillionth of a second, the usual laws of physics begin to break down. This is where a strange and eerie mystery begins. The Planck scale, named after the physicist Max Planck, represents a limit beyond which our understanding of space and time starts to fall apart. It defines the smallest possible measurement of length or time, a region where quantum effects become so intense that space itself might become foamy and unpredictable. At this scale, the effects of quantum gravity, the elusive connection between quantum mechanics and general relativity, can no longer be ignored. And this is where the Transplanckian problem arises. In simple terms, the Transplanckian problem is the question of what actually happens beyond the Planck scale. As we approach or exceed this threshold, our current models of physics collapse. According to our theories, we can't even measure distances this small, yet something fundamental may be occurring in this unexplored territory. Some theories suggest that space-time itself might behave in unexpected ways at this scale, or that particles might lose their familiar properties and behave in entirely unpredictable manners. Could this be the realm where quantum mechanics and gravity finally come together in harmony? The Transplanckian problem remains an open question, one that could hold the key to understanding how the universe truly works on the most fundamental level. As scientists continue to push the boundaries of physics, we may be getting closer to an answer. Hidden in a space so tiny it almost defies reality, the mystery persists. And so, we are left to wonder, what lies beyond the Planck scale? Causality violations in quantum mechanics. In the strange and often counterintuitive world of quantum mechanics, reality behaves in ways that defy our everyday understanding. One of the most perplexing features of quantum physics is its apparent tendency to violate causality, the principle that causes must always precede their effects. This phenomenon challenges our most fundamental assumptions about time, space, and the structure of the universe. Causality is a foundational concept in classical physics. It's also something we intuitively rely on in daily life. You flip a light switch, and the light turns on. Cause and effect follow a predictable order. But quantum mechanics, which governs the behavior of subatomic particles, seems to overturn this familiar logic. In certain quantum experiments, particles appear to know about future events before they occur. One striking example is quantum entanglement, where two particles become linked in such a way that a change to one instantly affects the other, regardless of the distance between them. This phenomenon, famously described by Einstein as a spooky action at a distance, seems to violate the conventional flow of time and suggests that information could, in some sense, travel backward. Even more bizarrely, some interpretations of quantum theory propose that particles may actually move backward in time or influence events that have already taken place. Imagine the possibility of sending a signal into the past or altering something that has already happened. These are the kinds of mind-bending ideas researchers encounter when exploring causality violations in quantum mechanics. The implications of these phenomena are profound. If causality can be broken at the quantum level, it might open the door to concepts like time travel or offer new insights into the true nature of time itself. Is time merely an illusion? Could it be more complex than we have ever imagined? And if causality does not hold in the quantum realm, what does that mean for our broader understanding of the universe? The mystery of causality violations in quantum mechanics forces us to confront the boundaries of our knowledge about time, space, and reality itself. Perhaps the universe is even more unpredictable than we once believed. Though the answers remain elusive, each new experiment adds another piece to the puzzle and deepens the mystery. Klein-Gordon and the mystery of negative probability. In the world of physics, there are many strange phenomena that challenge our understanding of reality. One of the most mind-bending of these is the concept of negative probability, a notion tied to a fundamental equation known as the Klein-Gordon equation. The Klein-Gordon equation is a mathematical framework used to describe particles, especially those moving close to the speed of light, such as bosons. It serves as a cornerstone of quantum field theory, which outlines how particles interact and evolve across space and time. However, when scientists began to examine this equation more closely, they stumbled upon a puzzling result. Under certain conditions, the equation produces negative values for probability. In classical physics, this is considered impossible. Probability is always a positive value, representing the likelihood of an event, like rolling a die or predicting the weather. A probability less than zero makes no sense within traditional frameworks. Quantum mechanics, however, is far more nuanced. In some quantum systems, applying the Klein-Gordon equation can lead to calculations that yield negative probabilities. This raises an unsettling question. Can negative probabilities actually exist? At first glance, the idea seems absurd. How can the chance of something happening be less than nothing? Yet physicists remain divided on the issue. Some propose that negative probabilities could hint at undiscovered aspects of physics, possibly pointing toward deeper forces or hidden layers of reality. Others argue that these results are not physically meaningful, but rather artifacts of how the equation is formulated or interpreted, mathematical quirks rather than reflections of the real world. What makes the Klein-Gordon negative probability problem so fascinating is its potential significance. Could this strange anomaly be a clue to a more complete understanding of the universe? If negative probabilities hold any real meaning, they could lead us to entirely new dimensions of physics, realms we have yet to fully comprehend. The mystery remains unsolved, but it fuels curiosity and inspires further exploration. The mere possibility of negative probabilities challenges our assumptions and forces us to ask, how much of reality is still waiting to be discovered? As the search for answers continues, so does the potential to rewrite the very laws of physics as we know them, perhaps even confronting ideas as radical as causality violations in quantum theory. The Woodward effect, a mystery that could change everything. The Woodward effect could redefine our understanding of motion and interaction in the universe. It centers around a fascinating and still unproven idea proposed by physicist James Woodward, the possibility of generating thrust without any conventional means of propulsion. No exhaust, no fuel, just pure motion. If this phenomenon turns out to be real, it could revolutionize space travel. James Woodward's hypothesis suggests that certain objects might experience a measurable force, a push, through the manipulation of energy and mass, without ejecting any material. This force, now known as the Woodward effect, seems impossible at first glance. But according to Woodward, it might be achievable by exploiting tiny fluctuations in mass. The core of the theory relies on a concept called mass fluctuations. Woodward proposed that under specific conditions, such as the application of electromagnetic fields, an object's mass could momentarily change. If timed and controlled precisely, these fluctuations could create an imbalance that results in a net thrust. In essence, the object could move forward simply by manipulating the surrounding forces without needing traditional propellants. Despite the groundbreaking potential, the Woodward effect remains highly controversial. While some experiments have reported small, unexplained forces, the results are often inconsistent and difficult to reproduce. Scientists are left asking, Is this a real effect, or just the result of measurement errors or unknown variables? What makes the Woodward effect so captivating is its profound implication. If validated, it could enable spacecraft to travel without massive fuel tanks or rocket engines. This opens the door to faster, more efficient space exploration, even interstellar travel. As of now, the Woodward effect is still an unsolved mystery. But whether it leads to a technological breakthrough or simply expands our scientific curiosity, it challenges the very foundation of our understanding of physics. The search for answers continues, and the journey, much like the potential of the Woodward effect itself, is both thrilling and full of mystery. The impossible M drive. Imagine traveling across the stars without the need for traditional fuel. No massive engines, no enormous fuel tanks. Just a small, mysterious device generating thrust seemingly out of nowhere. This is the astonishing promise of the M drive, a concept that sounds like something straight out of science fiction. In 2001, British engineer Roger Shire introduced the world to the M drive, a device that, if proven to work, could revolutionize space travel as we know it. The intrigue surrounding the M drive stems from its claimed ability to produce thrust without expelling any propellant. Traditional propulsion systems, such as rockets, operate by pushing against expelled gases or particles. This principle is rooted in Newton's third law of motion. For every action, there is an equal and opposite reaction. The M drive, however, appears to defy this fundamental rule of physics. It supposedly generates thrust using microwave radiation contained within a sealed, conical cavity. Despite lacking any conventional fuel or exhaust, the device seems to move forward, suggesting a potential violation of the law of conservation of momentum. Naturally, the scientific community was highly skeptical. Many experts proposed that any observed thrust could simply be the result of experimental error or external interference. However, in 2014, a team of researchers at NASA's EagleWorks laboratory decided to test the M drive for themselves. To their surprise, they recorded a small but measurable amount of thrust emanating from the device. This unexpected result suggested that something unusual might indeed be happening. Despite this tantalizing evidence, the underlying mechanism of the M drive remains a mystery. How can it generate thrust without violating the known laws of physics? Some theorists speculate that the device might be tapping into unknown aspects of quantum mechanics or interacting with the fabric of spacetime itself. The M drive continues to puzzle scientists, leaving the scientific community both excited and cautious. If it truly works, it could open the door to interstellar travel and dramatically alter humanity's future in space. However, until its physics are thoroughly understood and independently verified, the M drive remains one of the most fascinating and controversial enigmas in modern physics, a potential breakthrough waiting to be unlocked. The N-rays controversy. In the early 20th century, a French physicist named Blondlot claimed to have discovered a new form of radiation, which he called N-rays. He believed these rays were a type of invisible light emitted by all matter. Blondlot's findings quickly captured the excitement of the scientific community, with many seeing them as a potential breakthrough that could explain various unknown phenomena. However, as rapidly as N-rays rose to prominence, they were engulfed in one of the most baffling and mysterious controversies in scientific history. Blondlot and his team observed that certain materials, such as metals and crystals, seemed to emit these N-rays under specific conditions. He even designed experiments to detect the rays, reporting changes like variations in the brightness of light bulbs or shifts in material properties when exposed to N-rays. But soon, a troubling issue emerged. When other scientists attempted to replicate Blondlot's experiments, they couldn't produce the same results. Despite meticulously following his methods, N-rays remained elusive. What was happening? Was this truly a scientific breakthrough, or was there something else at play? The controversy deepened when an American physicist, John Abrahamson, attended one of Blondlot's demonstrations. Secretly, he removed a crucial component of the experimental setup, a prism that was supposed to detect N-rays. Yet Blondlot continued to report seeing the same effects, even without the prism. This led to serious doubts about the existence of N-rays. Eventually, Blondlot admitted that his results might have been influenced by the placebo effect or his own expectations. The N-ray mystery posed a chilling question. How could scientific discovery be so easily clouded by belief and expectation? The controversy surrounding N-rays serves as a cautionary tale, underscoring the importance of skepticism, verification, and the dangers of confirmation bias in the pursuit of knowledge. The ultraviolet catastrophe, historical overview. At the turn of the 20th century, physics was on the verge of a groundbreaking transformation. However, in 1900, a perplexing problem nearly halted the entire field. This issue became known as the ultraviolet catastrophe, and it has intrigued scientists ever since its discovery. The story begins with a scientist named Max Planck, who was attempting to understand how objects emit light. At the time, scientists believed they could calculate the intensity of radiation emitted by objects based on their temperature. But when they applied the formulas, something strange occurred with shorter wavelengths, like ultraviolet light. The calculations predicted an infinite amount of energy, which was obviously impossible. This was the catastrophe. The existing theory had broken down, and it appeared as if the entire framework of physics was on the verge of collapse. According to the classical physics of that time, as the wavelength of light shortened, the intensity of the radiation should increase without bound. However, everyday objects, like the sun, do not emit an infinite amount of energy. Instead, they emit light in a more controlled and measured way. So why was classical physics failing? The mystery was eventually solved by Planck himself. He proposed a revolutionary idea. Energy is emitted in discrete chunks, which we now call quanta. This notion contradicted everything that physics had previously believed. Despite initial resistance to his theory, Planck's idea marked the birth of quantum mechanics, a field of science that would eventually transform our understanding of the universe. The ultraviolet catastrophe exposed a major flaw in classical physics, pushing scientists to develop new theories. It was a pivotal moment that ignited the quantum revolution, leading to discoveries that fundamentally reshaped our knowledge of energy, light, and matter. What began as a perplexing issue in the realm of ultraviolet light eventually sparked a deep exploration of the very foundations of the universe. The ultraviolet catastrophe didn't just resolve a theoretical problem. It opened the door to an entirely new chapter in the history of physics. Non-quantized redshift travels across vast, unimaginable distances, carrying vital information about the stars and galaxies it encounters. One of the primary tools scientists use to understand the cosmos is redshift. This phenomenon occurs when light from distant objects appears stretched or shifted towards the red end of the spectrum, a result of objects moving away from us. Typically, redshift serves as a key indicator of the universe's expansion. However, a peculiar mystery has recently emerged, challenging everything we thought we knew about redshift. Non-quantized redshift. Normally, the redshift observed in light from distant galaxies is predictable and smooth. The farther away a galaxy is, the greater the redshift. But recently, scientists have begun to notice something unusual. Some galaxies appear to exhibit redshifts that don't follow the expected pattern. Rather than showing a smooth, continuous change, these galaxies show discrete jumps in their redshift values, as though they are shifting from one quantum level to another. This is what is known as non-quantized redshift. So what does this mean? Redshift is typically seen as a simple consequence of the universe's expansion, light being stretched as it travels through space. But if redshift isn't quantized, it suggests that there could be something else at play. Perhaps there is a new force or a hidden pattern in the structure of the universe that we have yet to uncover. Some theorists even speculate that these sudden shifts in redshift could be evidence of cosmic-scale phenomena, such as interactions between galaxies or even the influence of dark matter. The mystery of non-quantized redshift challenges our understanding of the universe's expansion. If redshift is behaving in unexpected ways, it might point to deeper, more fundamental aspects of spacetime itself. Could this be the beginning of a breakthrough? Might we be on the verge of discovering something profound that redefines our place in the cosmos? The search for answers continues, along with the possibility of uncovering new mysteries hidden within the very fabric of the universe. The Pioneer Plaque Misinterpretation Hypothesis. In 1972, a bold message was sent into the vast reaches of space in an attempt to communicate with any intelligent life beyond Earth. The Pioneer plaque, affixed to the Pioneer 10 spacecraft, depicted a human figure, an outline of our solar system, and a message designed to convey our existence to extraterrestrial beings. However, what if this well-meaning attempt was misinterpreted, resulting in an eerie mystery? The design of the plaque was carefully crafted by scientists Frank Drake and Carl Sagan to be universal, using simple pictorial symbols. But what if these symbols, meant to be understood across the vast expanse of space, could be interpreted in entirely different ways by an alien civilization? Could the symbols on the Pioneer plaque, rather than serving as a universal message, become an unintelligible puzzle? This forms the basis of the Pioneer Plaque Misinterpretation Hypothesis. Assumptions and challenges. One of the primary assumptions behind the plaque is that extraterrestrials would interpret symbols in the same way humans do. But what if the aliens do not share our understanding of symbols? Civilizations, whether on Earth or in distant galaxies, could have vastly different ways of interpreting images or symbols. For example, the depiction of a human figure on the plaque assumes that extraterrestrial beings would recognize and comprehend the human form. However, they may perceive something entirely different. Could they interpret the human figure as a symbol of hostile intent or as an invitation for contact? Such a misinterpretation could provoke unintended and unpredictable consequences. Furthermore, the plaque's instructions regarding Earth's location within the solar system might be unclear or perplexing. The message assumes that the recipient would understand certain astronomical concepts, but these might be beyond the grasp of a non-human civilization. If such concepts are not universally known, the message could easily lead to confusion or complete misunderstanding. The unsettling possibility. This hypothesis presents an unsettling possibility. The Pioneer plaque, instead of serving as a hopeful bridge to the stars, may inadvertently convey an enigmatic message that raises more questions than it answers. Could the search for alien life result in unintended and incomprehensible misunderstandings? As the Pioneer plaque continues its journey through space, it may carry more than just our message. It could also serve as a reminder that communication across such vast distances is fraught with uncertainty. Fractal Universe Hypothesis. The fractal universe hypothesis proposes a radically different view of the cosmos. What if the universe, while vast and immeasurable in scale, isn't simply expansive, but instead is infinitely detailed, with repeating patterns occurring at every scale, no matter how large or small? This is the intriguing possibility behind the fractal universe hypothesis. Fractals are geometric patterns that repeat at various scales. Consider the example of a tree. Its branches branch out into smaller ones, which in turn branch into even smaller ones, and so on. The shape remains similar regardless of how closely you look at it. Fractals are abundant in nature, from clouds and mountains to coastlines, and in mathematics, they exemplify a form of self-similarity. The fractal universe hypothesis suggests that the entire universe might operate in a similar fashion, with patterns repeating at every scale, from the tiniest particles to the largest galaxies. On the surface, this concept might seem too abstract to be true. How could such an enormous, complex universe follow a simple, repeating pattern? Yet, some physicists argue that the fractal nature of the universe could potentially explain many of its most perplexing features. For example, the distribution of galaxies in the universe isn't perfectly uniform. Instead, galaxies tend to form clusters, with vast voids in between, which resemble the branching structures of a fractal. This self-similarity across different scales could point to a hidden pattern in the cosmos. Perhaps the most captivating aspect of the fractal universe hypothesis is the possibility that, just as fractals never end in complexity, the universe itself might not have a true boundary or end. Instead, it could continue to scale infinitely, with similar structures repeating endlessly as we look deeper into the cosmos, or even deeper into the very fabric of space itself. This idea raises profound questions. Could the universe be an intricate pattern that we have yet to fully comprehend? If the cosmos is indeed fractal, we might be witnessing an infinity of universes, each waiting to be discovered. While the mystery remains unresolved, the very thought invites us to explore the structure of everything we know, challenging our understanding of the universe's true nature. Emergence of consciousness and physics. The idea that something as complex as consciousness, which enables us to think, feel, and experience the world, could be explained by the fundamental laws of physics, might sound like the premise of a science fiction novel. However, some scientists believe that the emergence of consciousness may actually be linked to the very fabric of the universe itself. At its core, the concept of consciousness emerging refers to the notion that complex systems, like the human brain, can give rise to conscious experience through the interaction of simpler components. In other words, consciousness may not be a unique or special property of the mind, but rather a phenomenon that naturally emerges from the intricate web of physical processes within the brain. However, this concept raises an intriguing question. Can consciousness be fully explained by the laws of physics alone? Physicists and neuroscientists have been exploring this idea for decades, but the connection between consciousness and the fundamental laws of physics remains elusive. For centuries, the physical processes of the brain, the firing of neurons, the transmission of chemical signals, have been studied in great detail. Yet the how and why of consciousness, why the brain's activity results in subjective experience, remains a profound mystery. This is where quantum mechanics enters the conversation. Some scientists believe the key to understanding consciousness might lie in the strange behavior of particles at the quantum level. Certain theories suggest that quantum effects in the brain's microtubules, tiny structures found inside neurons, could be central to the emergence of human awareness. This intersection of consciousness and physics raises a mind-bending question. Is consciousness merely a byproduct of complex physical interactions, or is it something more profound? Could it be that the very structure of the universe contains the blueprint for consciousness itself? The search for answers is ongoing, but the mystery remains. Is consciousness just another physical phenomenon, or does it transcend the known laws of physics? Cosmic inflation instability. At the very beginning of the universe, something extraordinary occurred. In a fraction of a second, the entire cosmos expanded at an unfathomable rate. This event, known as cosmic inflation, set the stage for everything we observe today. However, there lies an intriguing mystery about this expansion. Could the very process that birthed the universe also make it unstable? Cosmic inflation is a theory that posits, shortly after the Big Bang, the universe expanded exponentially faster than the speed of light. This rapid expansion smoothed out the cosmos, resulting in the uniform structure we see in galaxies and stars. It is a widely accepted concept in cosmology. Yet, there's an unsettling aspect to this theory. Inflation might not be as stable as we believe. Some scientists suggest that the inflationary process could, in theory, trigger an instability in spacetime. This instability might lead to regions of the universe undergoing another burst of rapid inflation, creating new pocket universes or even altering the fundamental nature of our own universe. These pockets could exist independently, each with its own set of physical laws and properties, potentially making our universe just one bubble in an expansive cosmic foam. If such an instability exists, it raises a chilling question. Could it ever affect us? If the bubble of our universe were to pop or shift, what would happen to everything inside it? While this is purely speculative for now, the notion that our universe might not be as stable as it seems adds a haunting dimension to the story of cosmic inflation. The mystery of cosmic inflation instability isn't just about understanding the universe's past. It's about questioning whether our existence is more fragile and intricately connected to the deeper workings of the cosmos than we ever imagined. The arrow of time paradox. We all experience the passage of time, always feeling its constant flow forward. But what if that flow isn't as simple as it seems? What if the arrow of time, the direction in which time flows, isn't as straightforward as we believe? The arrow of time paradox is one of the most puzzling enigmas in physics. It refers to the concept that time has a distinct direction. Events unfold in one specific order, from past to present to future. We remember the past, not the future. We see objects break down, like a glass shattering, but never spontaneously reassemble. This one-way flow of time feels natural to us, yet it raises a profound question. Why does time seem to move in only one direction? In physics, the fundamental laws of nature, such as those governing motion or gravity, do not prescribe a specific direction for time. These laws are time-symmetric, meaning they function the same whether time is moving forward or backward. So, why then does time always seem to move forward? Why do we never experience a moment where time flows backward, reversing decay and chaos? The answer seems to lie in a concept called entropy. Entropy is a measure of disorder or randomness. As time progresses, systems tend to evolve from order to disorder, like ice melting into water or a room becoming messier over time. This increase in entropy provides a sort of arrow pointing time forward, guiding it in one direction. But here's the strange part. While this helps explain why time feels like it only flows in one direction, it doesn't answer the deeper question of why time is intrinsically linked to entropy in the first place. The arrow of time paradox continues to perplex scientists, leading to further investigation. It is not just a question about the physics of time, but also about how we perceive and experience reality. Could the flow of time be more mysterious than we understand? The answer remains elusive, suggesting that there may be even deeper questions about the nature of the universe waiting to be uncovered. Vacuum decay, the mysterious concept of the universe's stability. Imagine the universe as a calm, stable place, where everything seems to follow predictable rules. But what if that stability could suddenly collapse, altering everything we know in an instant? This unsettling possibility is known as vacuum decay, one of the most mysterious and mind-bending concepts in modern physics. Vacuum decay is a theoretical event that could occur at any moment, though scientists believe it is highly unlikely. The idea is that our universe, which appears stable, might not actually be in its lowest energy state. To understand this, picture a marble resting at the bottom of a bowl. The marble stays at the lowest point, but what if the bowl itself were unstable? The marble could fall into a completely different, deeper state, one that destroys everything in the process. In physics, this deeper, unstable state is referred to as a false vacuum. According to quantum field theory, the vacuum of space isn't truly empty, it's filled with energy. However, this energy might not be in the absolute lowest possible state, and the universe could shift from this false vacuum into a true vacuum. If that were to happen, It would trigger a chain reaction that would change the very laws of physics as we know them and possibly wipe out the current structure of space and time. The most unsettling aspect of vacuum decay is that it could happen without warning. It's not something we could predict or see coming. When it does occur, the shift would spread at the speed of light, obliterating everything in its path. While this may sound like science fiction, scientists take it seriously because it's grounded in real principles of quantum mechanics. Fortunately, the likelihood of vacuum decay happening anytime soon is extremely low. However, the mere possibility challenges our understanding of the universe's stability and leaves us with a chilling question. Is the universe really as stable as it seems? Phantom energy, the vastness of uncertainty. In the vastness of the universe, questions like this make us reconsider what we think we know about reality. Phantom energy. Something strange is happening in the vast expanse of space, an invisible yet incredibly powerful force that scientists have named phantom energy. This mysterious energy may hold the key to one of the greatest mysteries of the universe. Phantom energy is a force that seems to be accelerating the expansion of the universe. While it has been known for some time that the universe is expanding, the surprising twist is that it's expanding at an ever-increasing rate, not slowing down as was once believed. This unexpected acceleration is driven by dark energy, a force that makes up about 70% of the universe. However, phantom energy takes this concept even further. It is a form of dark energy that could be even more potent, causing the universe's expansion to speed up faster and faster over time. The idea of phantom energy raises an eerie possibility. What if the universe is expanding so rapidly that galaxies and stars will eventually be pulled apart, unable to interact with each other ever again? It would be as if the very fabric of space itself were tearing apart. Phantom energy could be the force behind this catastrophic event. Scientists are still working to understand the nature of phantom energy. It might be related to a phenomenon called the cosmological constant, a term that was introduced by Albert Einstein in his equations for general relativity. However, phantom energy suggests that the rate of acceleration could continue to increase indefinitely, leading to a scenario known as the Big Rip, where the universe would tear itself apart at the seams. The mystery of phantom energy leaves us with more questions than answers. Is it just a temporary phase in the universe's life, or will it eventually result in a dramatic and irreversible end? As scientists continue to study the behavior of dark energy and phantom energy, they are uncovering a hidden force that could completely change our understanding of the universe's fate. The Great Attractor Mystery. Galaxies, stars, and planets abound in the universe, but there exists one strange and mysterious force that seems to be pulling the entire cosmos toward a single, elusive point. This point is known as the Great Attractor, and its influence has confounded scientists for decades. The Great Attractor is a massive gravitational anomaly located within a region of space known as the Laniakea supercluster, a vast collection of galaxies that includes our own Milky Way. Here's the enigma. No one knows exactly what the Great Attractor is. It's hidden behind the zone of avoidance, a region of space where our view is obstructed by the dense plane of our own galaxy. So, despite the fact that we can feel its gravitational pull, we cannot directly observe it. What we do know, however, is that it's pulling galaxies, including ours, toward it at an astonishing speed of over 2 million kilometers per hour. Imagine attempting to escape a force so powerful that it drags entire galaxies through the vastness of space. But what exactly is causing this immense pull? Some theories suggest that it could be a supermassive black hole at the core of a colossal galaxy cluster, exerting an enormous gravitational force. Others propose that it could be a concentration of galaxies so massive and dense that their combined gravity is warping space-time itself. Despite these theories, the true nature of the Great Attractor remains a mystery. Is it merely a massive, unseen object? Or could it be something far more complex? Something that challenges our current understanding of the universe? The Great Attractor raises fundamental questions about the limits of our knowledge. If it is truly exerting such a force on everything around it, might there be other hidden forces in the cosmos, waiting to be discovered? As astronomers continue to study this strange and captivating phenomenon, the Great Attractor remains one of the most fascinating and unresolved puzzles in modern physics. Dark flow. In the vast expanse of the cosmos, galaxies are generally moving apart as the universe expands. However, what if something mysterious was causing them to shift in a completely unexpected direction? This is the puzzling phenomenon known as dark flow. Dark flow was first detected in 2008 when scientists noticed that galaxies, especially those located at the farthest reaches of the observable universe, were not following the expected patterns of cosmic expansion. Instead, they appeared to be drifting toward a specific point in space. This motion didn't align with our current understanding of the universe's expansion, leaving scientists baffled. What could be causing such an unusual movement? The most intriguing aspect of dark flow is that it doesn't seem to be influenced by any known forces, such as the gravitational pull from nearby galaxies or clusters. Some scientists speculate that it may indicate the presence of a massive, unseen structure in the universe, one too distant to be detected with current technology, which is exerting a pull on everything around it. This mysterious force could be a supermassive galaxy cluster or another unknown cosmic structure, something that challenges our comprehension of the universe's behavior on its largest scales. What makes dark flow even more perplexing is that it could hint at the existence of regions beyond the observable universe, areas that lie beyond the reach of our current technological capabilities. This opens up a tantalizing possibility. Could there be unknown forces, hidden galaxies, or even entire universes beyond our perception? Dark flow raises unsettling questions, suggesting that there may be far more to the universe than we are currently aware of. A force, beyond our understanding, could be guiding galaxies in ways we cannot fully explain. As scientists continue to investigate this enigma, it's becoming increasingly clear that the universe still holds many secrets waiting to be uncovered. The supervoid in Eridanus. Imagine gazing into the vastness of the universe, expecting to see a sea of galaxies and stars, only to be met with an eerie emptiness, a vast gap where almost nothing exists. This is what scientists encountered when they discovered the supervoid in Eridanus, one of the largest known voids in the universe. The Eridanus supervoid is an immense, almost incomprehensible emptiness in space, stretching across an astonishing 1.8 billion light-years. In this area, very few galaxies are found, creating what could be described as a cosmic desert. But what truly adds to the mystery of this void is what it might be concealing. While it's clear that the supervoid is largely devoid of matter, the big question remains: what is causing such a vast region of space to be so empty? The most intriguing aspect of this supervoid is its unusual effect on the cosmic microwave background radiation, the faint afterglow of the Big Bang. When scientists measured this radiation, they discovered that the supervoid appeared to be distorting it. The temperature in this region is slightly lower than in other areas, suggesting that the void could be influencing how energy behaves over vast distances. Some theories propose that the void's creation could be due to gravitational effects, with massive structures outside the void pulling on the fabric of space. Others speculate that there may be a more mysterious explanation, perhaps linked to the nature of dark energy or the overall structure of the universe. The Eridanus supervoid challenges our understanding of the cosmos. It's a cold, seemingly lifeless region, but its very existence compels us to ask deeper questions about the shape, structure, and ultimate fate of the universe. What might be hidden within this cosmic emptiness? The answers remain an intriguing and unsettling mystery. Evidence of bubble universes colliding. In the vast expanse of the cosmos, the universe we know might just be one of many possible worlds. What if, hidden within the fabric of space itself, there exist other universes, each a bubble floating alongside ours? And what if these bubble universes actually collided? This concept represents one of the most mind-bending mysteries in modern physics: the potential evidence of bubble universes colliding. The theory of bubble universes originates from a concept known as eternal inflation. According to this theory, after the Big Bang, the universe didn't expand uniformly. Instead, certain regions of space began to inflate at an astonishing rate, leading to the formation of separate bubbles of space-time. Each of these bubbles could have distinct laws of physics, different constants, and even alternate dimensions. Some bubbles might still be growing today, while others could have already popped or merged with one another. In 2007, scientists believe they might have discovered evidence of a bubble universe collision. They noticed unusual patterns in the cosmic microwave background, CMB, the faint afterglow of the Big Bang, that seemed to indicate a massive impact. These anomalies, such as unexpected hot or cold spots in the radiation, suggested that another universe had collided with ours, leaving an imprint of the event in the very fabric of space. This discovery, if confirmed, could radically shift our understanding of the universe. The existence of bubble universes implies that our universe might not be unique. If we find evidence of a collision, it would point to a vast multiverse, an infinite reality where other universes not only exist, but can also interact with one another. The idea of bubble universes colliding challenges everything we know about space-time and existence itself. Although the evidence is still under debate, it opens a window into a mystery that could change the way we perceive reality. Are we simply one bubble in an infinite ocean of universes, each potentially on the brink of colliding with the unknown? The strange cold spots observed in the cosmic microwave background could be a clue to the truth that awaits discovery. The cold spot in the cosmic microwave background. The cosmic microwave background, CMB, is the faint afterglow of the Big Bang, a relic radiation that offers a snapshot of the early universe. Scientists expected it to be a smooth, uniform sea of radiation. However, in 2004, they discovered something far more mysterious: a vast cold spot. This region, significantly colder than the surrounding areas of the CMB, was larger than anticipated and immediately raised profound questions. What could possibly explain such a strange anomaly? The CMB is a critical tool for understanding the origins and evolution of the universe. So, when researchers noticed this unusual cold region, it initially seemed like a minor statistical fluctuation. But as more precise data became available, the anomaly persisted, and scientists began to suspect that something far more unusual might be at play. Some theories suggest that the cold spot could be linked to cosmic inflation, the rapid expansion of the universe immediately following the Big Bang. However, more speculative and mind-bending ideas have also emerged. One particularly fascinating hypothesis is that the cold spot might be evidence of a parallel universe. According to this theory, our universe may have collided with another bubble universe in the distant past, leaving an imprint in the CMB that we now observe as the cold spot. Despite extensive study, the true cause of the cold spot remains unknown. Some researchers believe it could simply be an unexpected variation from the early universe's natural fluctuations, while others continue to explore more extraordinary possibilities. Regardless of its origin, the cold spot stands as one of cosmology's most intriguing puzzles. It challenges our understanding of the cosmos and invites scientists to reconsider the very nature of the universe, and even the possibility that other realities might exist beyond our own. This mystery also ties into another strange feature in the CMB known as the axis of evil, adding yet another layer to the enigma of our universe. The axis of evil, cosmic microwave background anomaly. To better understand the origins of the universe, scientists have studied the cosmic microwave background, CMB, the faint afterglow left behind by the Big Bang. This radiation is one of our most valuable tools in uncovering the universe's earliest secrets. However, in 2005, astronomers made a surprising discovery within the CMB, a strange and unexpected alignment in the data. This anomaly would later be referred to as the axis of evil. The CMB is generally uniform, evenly spread across the sky, as one might expect from a massive and chaotic event like the Big Bang. Yet, the axis of evil revealed an unusual pattern, an alignment of temperature fluctuations that seemed anything but random. Instead, these variations appeared to line up along a specific axis, almost as if an invisible force was tugging on the very fabric of space. What makes this discovery so unsettling is how precise the alignment appears. It seems too perfect to be the result of chance. This observation contradicts the predictions made by the well-established theory of cosmic inflation, which holds that the universe should be isotropic, uniform in all directions. Some scientists have speculated that this anomaly might be the result of an unknown systematic error in the measurements. However, it's challenging to explain how such an error could produce such a large-scale and consistent pattern. Others have ventured into more speculative territory, proposing that the axis of evil might hint at something far deeper, possibly even a connection between our universe and another. There are also theories suggesting that this phenomenon could point to physics beyond the standard model of cosmology, challenging our fundamental understanding of the cosmos. Although the true nature of the axis of evil remains a mystery, it continues to intrigue and unsettle physicists. It serves as a powerful reminder that even in our most carefully measured observations, there is still much about the universe we don't fully understand. And whatever we discover next could change everything. White holes. White holes are a fascinating and mysterious concept in physics. Unlike black holes, which have gravity so intense that they pull in everything around them, including light, white holes are thought to do the opposite. Instead of swallowing matter and energy, they would expel it, acting like cosmic fountains. White holes are purely theoretical and were first predicted by the equations of general relativity, the same framework that describes black holes. While black holes have an event horizon, a boundary beyond which nothing can escape, white holes are theorized to have a boundary that nothing can enter. In this sense, they are the reverse of black holes. The idea of a white hole arises naturally from the mathematics of black holes. If you reverse the flow of time in the equations that describe a black hole, the result is a white hole. Whereas black holes pull everything inward, white holes would push everything outward, creating a strange paradox. How could matter and light escape from a region that, according to general relativity, should be completely sealed off? This is where the mystery deepens. Unlike black holes, which have been observed in the universe, white holes have never been detected. This raises a major question. Do they actually exist, or are they merely mathematical curiosities? Some theories propose that white holes might be linked to wormholes, tunnels through space-time that connect distant parts of the universe, or even different universes entirely. In certain models, a white hole could represent the other end of a black hole, meaning matter that falls into a black hole might emerge from a white hole elsewhere in space. Despite these intriguing possibilities, there is still no direct evidence of white holes. They remain one of the most captivating mysteries in modern physics, pushing the boundaries of what we understand about the universe. Could white holes exist in the farthest reaches of space, or are they simply the result of equations we don't yet fully comprehend? For now, the mystery continues. The information paradox of black holes. Imagine dropping a book into a black hole. The book disappears, sucked into the abyss, seemingly gone forever. But here's the strange and puzzling question. Where did the information contained in that book go? This is the heart of the information paradox of black holes, one of the most perplexing mysteries in modern physics. According to the laws of quantum mechanics, information about a physical system, like the details written on the pages of that book, can never be truly lost. Even if the system changes or is destroyed, the information must, in theory, still exist in some form. However, black holes appear to break this rule. When matter falls into a black hole, it seems to vanish completely, with no trace of its original state remaining. The black hole absorbs it, and all information about its past form appears to be erased. This presents a major problem because it violates a fundamental principle in quantum physics known as unitarity, which states that information must always be preserved. For decades, this paradox has baffled scientists. On one side, we have the well-established laws of quantum mechanics insisting that information cannot be lost. On the other side, we have the solid framework of general relativity, which describes black holes as objects that destroy information forever. This conflict highlights a deep rift between the two pillars of modern physics, general relativity and quantum mechanics. Several theories have been proposed in an attempt to resolve the paradox. One idea is the holographic principle, which suggests that all the information falling into a black hole is actually stored on its two-dimensional surface, like a cosmic hologram. Another proposal involves Hawking radiation, a theoretical process through which black holes slowly evaporate over time. Some physicists believe that information might gradually leak out through this radiation, although the mechanism remains unclear. While no definitive solution has yet been found, the information paradox forces scientists to question the very foundations of physics. Is information truly lost forever inside a black hole? Or is there a deeper, hidden layer of reality we've yet to discover? The answer could change everything we know about the universe, including our understanding of space, time, and the fundamental nature of existence itself. Black hole firewalls. When we think of black holes, we often picture the event horizon, the point of no return, where nothing, not even light, can escape. But what if crossing that boundary wasn't just a one-way trip into darkness? What if, instead, a deadly, fiery wall awaited anyone who dared to enter? This chilling idea is at the heart of a mystery known as the black hole firewall paradox. The concept of a black hole firewall emerged from a deep theoretical puzzle in physics. According to Einstein's theory of general relativity, if you were to cross the event horizon of a black hole, you wouldn't notice anything unusual. From your perspective, it would feel like passing through an invisible boundary, with nothing remarkable happening, until, eventually, you'd be crushed by the extreme gravity of the singularity at the center. However, quantum mechanics tells a different, stranger story. In the quantum world, information can never be truly lost. But when matter crosses a black hole's event horizon, it appears to vanish forever, creating a conflict between two of the most important theories in physics. To resolve this contradiction, some physicists have proposed a radical idea. What if the event horizon isn't smooth and calm, but instead a blazing barrier of energy? This so-called firewall would instantly destroy anything that tries to pass through, preventing the loss of information. But this idea brings its own problems. If firewalls exist, they violate the very principle of quantum mechanics that forbids the destruction of information. On the other hand, if firewalls don't exist, we're left struggling to explain how information is preserved, challenging our understanding of both space-time and gravity. At the core of this paradox lies the tension between the laws that govern the universe on its largest scales, general relativity, and those that govern the tiniest particles, quantum mechanics. The black hole firewall paradox remains unsolved, but it is one of the most important clues in the quest for a unified theory of physics. What truly happens when something crosses a black hole's event horizon? The answer might unlock the secrets of the universe itself. The eternal inflation paradox. At the very beginning of the universe, there was a moment of rapid expansion known as cosmic inflation. In an instant, the universe grew from subatomic sizes to the vast expanse we observe today. But what if this inflation never actually stopped? What if, instead of settling into a stable state, the universe continued to expand forever? This idea lies at the heart of the eternal inflation paradox. Eternal inflation is a theory that suggests cosmic inflation didn't occur as a single, uniform event. Instead, it proposes that certain regions of space continue to inflate at different rates, indefinitely. This ongoing expansion creates countless bubbles of space-time, each potentially forming its own universe, possibly with its own unique laws of physics, constants, and structures. In this view, our universe could be just one bubble in an endlessly expanding multiverse. And this is where the paradox emerges. According to the eternal inflation model, new universes are constantly being born. This never-ending process seems to challenge our understanding of time and space. If space is inflating eternally, how can we ever fully measure or comprehend the true extent of reality? It suggests that what we perceive as the universe might be just a tiny fragment of a much larger and fundamentally unknowable system, one that stretches far beyond anything we can observe. Eternal inflation also raises a profound and unsettling question. If new universes are continuously forming, what becomes of the physical laws within them? Can our current understanding of gravity, matter, and energy remain valid in such a chaotic and constantly evolving cosmos? Ultimately, the eternal inflation paradox isn't just a theoretical dilemma. It's a deep challenge to the way we think about the origin, the nature, and the destiny of the universe itself. As scientists continue to explore this mind-bending concept, they may uncover a reality far more complex than anything we've ever imagined. The universe, it seems, might be less like a static structure and more like a living, evolving neural network of cosmic proportions. The universe as a neural network. What if the universe we inhabit isn't merely a vast collection of stars, planets, and galaxies, but something far more profound? What if, at its core, the cosmos functions like a neural network? This fascinating and mysterious idea proposes that the universe might operate in ways similar to how our brains process information. In simple terms, a neural network is a system of interconnected units or nodes, similar to neurons in the brain, that work together to process and transmit information. This concept forms the backbone of deep learning in artificial intelligence. Now, imagine the entire universe operating like such a network, billions of galaxies acting as individual neurons within a cosmic brain, continuously exchanging information and feedback. This theory isn't about comparing the physical shape of the universe to a brain, but rather about the possibility that the universe processes information through complex patterns and interconnections between seemingly unrelated parts. Some physicists have proposed that the fundamental laws and structures of the universe, from subatomic particles to the vast organization of galaxies, could function as elements in a vast information processing system. Much like a neural network, the universe might learn, adapt, and evolve over time. This idea is both mind-bending and deeply intriguing. Could the universe itself be thinking or learning in a way we have yet to comprehend? Could the fundamental forces of nature, like gravity or electromagnetism, be analogous to the synaptic connections that hold a cosmic neural network together? Some even speculate that consciousness might be an emergent property of this universal network, a byproduct of its intricate, evolving structure. While this theory remains highly speculative, it encourages us to consider the universe in a radically new light, not as a static backdrop for existence, but as a living, dynamic system actively processing information, much like our own minds. It's a mystery that compels us to wonder, is the universe learning? Is it evolving? And could it, in some unfathomable way, be aware of its own existence? The holographic universe hypothesis. What if everything you see, hear, and feel isn't truly real, but rather a projection of something more fundamental? This is the eerie and mind-bending suggestion behind the holographic universe hypothesis. Imagine that the entire universe we live in is like a three-dimensional hologram, a detailed illusion projected from information stored on a two-dimensional surface, possibly on the edge of a cosmic black hole or some other hidden dimension. While it might sound like science fiction at first, this concept has been seriously explored by theoretical physicists. The idea proposes that all the complex, three-dimensional reality we experience could actually be a projection, much like how a 3D holographic image is created from a 2D pattern. This perspective originates from the study of black holes and the very nature of space and time. In the 1990s, physicist Juan Meldacena introduced the holographic principle, a revolutionary idea suggesting that the entire universe could be encoded on a distant two-dimensional boundary, much like the surface of a black hole. Everything within this boundary, including space and time itself, may emerge from the way this information is stored and processed along the edge. Perhaps the most astonishing implication of this theory is that everything in our universe, every star, every planet, every living being, might be a mere illusion, a projection of data existing in a two-dimensional realm we cannot directly access or perceive. This raises profound questions. If reality is just a projection, why does it feel so real? Are we living in a sophisticated simulation? Or is the universe itself simply an intricate illusion created from fundamental data? Although the holographic universe hypothesis remains theoretical, it challenges the very core of how we understand existence, space, and reality. It invites us to consider, what if everything we know is just an image on a vast cosmic screen? Parent stability supernova. In the vast and mysterious depths of space, stars are born, live, and eventually die. But what happens when a star dies in an explosive, yet incredibly unusual way? This is where the phenomenon known as a parent stability supernova comes into play, one of the most powerful and puzzling events in the universe. Most stars end their lives in dramatic supernova explosions, collapsing into neutron stars or black holes. However, the most massive stars go out with an even more intense and extraordinary bang, an event so extreme that it challenges our very understanding of physics. A parent stability supernova occurs when a massive star, far larger than our Sun, reaches the final stages of its life. As it burns through the last of its nuclear fuel, the core becomes so hot and dense that it begins to produce something unusual, pairs of particles called electrons and positrons. At extremely high temperatures, these electron-positron pairs absorb energy, leading to a sudden and dramatic drop in pressure inside the star's core. This loss of pressure causes the star to become unstable. Unable to support its own weight, the star undergoes a catastrophic explosion. Unlike other supernovae, which often leave behind dense remnants like black holes, a parent stability supernova is so powerful that it completely tears the star apart, leaving nothing behind but a burst of energy and a fleeting flash of light. What makes this type of explosion so strange and fascinating is that it only occurs in the most massive stars, those dozens or even hundreds of times more massive than the Sun. Because of this, parent stability supernovae are extremely rare and difficult to observe. Even more intriguing is what happens to the elements forged during these violent explosions. These events create and scatter heavy elements such as gold and platinum, which go on to enrich the universe. These materials become part of new stars, planets, and eventually, life itself. The parent stability supernova gives us a glimpse into the violent, mysterious forces that shape the cosmos. It's a stunning reminder that the universe is filled with strange phenomena, many of which remain unexplained, just waiting to be discovered. Boundary conditions of the universe. The universe is constantly expanding, but a profound question lingers at the edge of scientific understanding. What are the boundary conditions of the universe? In other words, what limits or rules define the edges of space, time, and the very fabric of reality? This question is far from simple. We often imagine the universe as infinite, stretching endlessly in all directions. However, when scientists explore the origins and structure of the cosmos more deeply, they uncover a fascinating mystery. If the universe is expanding, what exactly is it expanding into? Is there a physical edge, or does it continue infinitely? And if the universe began with an event like the Big Bang, what were the conditions at the very moment space and time came into existence? One compelling theory suggests that the universe might have no boundaries at all. According to this idea, the universe isn't expanding into anything. Rather, space itself is stretching without any edge or center. This concept is connected to the idea of a closed universe, where space curves back on itself, similar to the surface of a sphere. In such a model, if you traveled far enough in one direction, you would eventually return to your starting point, just like walking around the Earth. But the mystery deepens. The concept of the multiverse raises even more questions. If there are multiple universes, do each of them have their own unique boundary conditions? Could our universe be just one bubble in a much larger and more complex cosmic system, one with rules and limits we cannot yet perceive or understand? These questions challenge our fundamental understanding of space, time, and reality itself. As scientists continue to study the origins of the universe, the search for answers to these profound mysteries could unlock a new chapter in our knowledge of existence. The boundaries of the universe, it seems, may be far more mysterious than we have ever imagined. Exotic vacuum objects. In the depths of space, there are strange and mysterious objects that defy everything we think we know about the universe. These objects are known as exotic vacuum objects, and they could be more enigmatic and dangerous than anything we have ever encountered. Exotic vacuum objects are theoretical cosmic phenomena that exist in what we once believed to be the empty vacuum of space. Contrary to this belief, the vacuum is actually filled with fluctuating energy, which can give rise to unusual and extreme states of matter, such as exotic vacuum objects. What makes these objects so eerie is that we do not fully understand how they work, nor are we certain they even exist. The concept is based on a process called vacuum decay, in which the vacuum of space, instead of being empty, could exist in different phases or states. Some theories propose that under the right conditions, these phases could lead to the creation of extremely dense and unstable objects, which could grow larger and more powerful, reshaping everything in their path. In some interpretations of this theory, exotic vacuum objects are imagined as cosmic bubbles of strange matter. These bubbles could expand, engulfing and altering the space around them. Picture an object that could fundamentally change the laws of physics as we know them, similar to a black hole, but not bound by the usual rules, and potentially capable of consuming everything in its path. The mystery surrounding these objects goes beyond simply trying to determine what they might be. It also raises questions about how they would behave if they actually existed. Would they collapse into a black hole? Would they vanish into nothingness? Could they be lurking in the farthest reaches of space, unseen, just waiting for the right conditions to emerge? While exotic vacuum objects remain hypothetical, their potential to challenge and expand our understanding of the universe is immense. They force us to ask profound questions. Is space truly empty, or are there hidden, unknown forces at work, shaping the cosmos in ways we cannot yet imagine? Tachyonic fields operate under specific rules. Things generally move at a certain speed, and forces act in predictable ways. However, what if there were particles that broke these rules and traveled faster than light? This idea lies at the heart of the tachyonic field mystery. Tachyons are hypothetical particles that, unlike anything we currently understand, could potentially travel faster than light. The concept was initially introduced in the context of quantum field theory, where tachyons were first imagined as particles with imaginary mass. What makes tachyons even more fascinating is the concept of the tachyonic field, a field that could exist throughout the universe, with these superspeed particles at its core. The mystery surrounding tachyons arises from their peculiar properties. According to Einstein's theory of relativity, nothing can travel faster than the speed of light in a vacuum. Therefore, if tachyons do exist, they would challenge this fundamental rule of physics. The real puzzle, however, isn't just whether these particles could exist. It's about what their presence could mean for our understanding of the universe itself. Tachyonic fields have also been suggested as a potential explanation for certain phenomena in theoretical physics, such as the inflationary period of the early universe, when space expanded at an unimaginable rate. Some scientists propose that these fields could have played a role in that rapid expansion, shaping how the universe evolved. The mystery deepens when considering the implications tachyons could have on the nature of time and space. If tachyons can move faster than light, could they also move backward in time? Could they hold the key to unlocking time travel, or even reveal entirely new dimensions of space? Although no concrete evidence of tachyons has been found yet, the idea continues to spark the imagination of physicists, hinting at potential breakthroughs that could push the boundaries of our current understanding of the universe. This mystery suggests there is far more to the cosmos than we have discovered so far, waiting just beyond the speed of light. Superluminal galactic jets. In the distant reaches of space, where galaxies spin and stars are born, something peculiar is occurring. Scientists have observed superluminal galactic jets, streams of particles shooting out from the centers of galaxies at speeds faster than light. Yes, faster than light. But how is this possible when, according to Einstein's theory of relativity, nothing can move faster than the speed of light? These galactic jets are powerful, high-energy streams of plasma, often emerging from the supermassive black holes at the hearts of galaxies. They can stretch across millions of light years, moving at incredible speeds. Some of these jets even appear to be traveling faster than light itself. However, there's an important caveat. The jets aren't actually moving faster than light in the traditional sense. Instead, their speed creates a visual illusion. The mystery behind this lies in a relativistic effect known as Doppler shifting. When objects move close to the speed of light, the light emitted from them is stretched or compressed, depending on their direction. If a jet is pointed directly toward us, its motion can appear to exceed the speed of light due to this effect, creating the illusion of superluminal speed. But in reality, the particles in the jet aren't surpassing the cosmic speed limit. They're simply moving so fast that they distort our perception of their velocity. Even with this explanation, the mystery persists. Why do these jets exist at all? What do their extraordinary energy and movement reveal about the behavior of matter around black holes? And what do they tell us about the laws of physics in extreme environments? The discovery of superluminal galactic jets challenges our understanding of space, motion, and gravity, reminding us that the universe operates in ways we are only beginning to comprehend. Quasi-stellar objects and quasars. The alignment of quasi-stellar objects, quasars. In the far reaches of the universe, there exist objects so distant and bright that they appear almost otherworldly. These are quasi-stellar objects, or quasars, and they have been a source of awe and mystery since their discovery in the 1960s. Quasars are extraordinarily powerful and energetic centers of distant galaxies, where a supermassive black hole is actively consuming surrounding material. The result is the emission of vast amounts of radiation, often outshining the entire galaxy combined. However, what truly baffles scientists is the strange alignment of these quasars. Many appear to be arranged in unexpected ways, pointing in peculiar directions, as if they were deliberately positioned. This alignment raises fascinating questions. Why do quasars seem to be arranged in this way? Some studies suggest that quasars may not be randomly distributed across the sky. Instead, they might be aligned along specific axes, pointing in directions that seem to defy the natural distribution patterns seen in galaxies. This observation has led to intriguing speculation. Could these alignments be the result of a hidden force at play in the universe? Or do they reveal something we still don't understand about how galaxies and black holes form? One possible explanation is that quasars might be aligned due to gravitational interactions between massive cosmic structures, such as galaxy clusters or dark matter. These interactions could influence the orientation of black holes in these galaxies, leading to an observable pattern of alignment. Yet the mystery deepens when we consider that these alignments occur across vast cosmic distances, far exceeding the scale of individual galaxies. Could there be an even more fundamental force at work, one that shapes the universe on a larger scale? The alignment of quasars challenges our current understanding of the cosmos, suggesting that there is still much we have yet to discover. Could the universe be more ordered and interconnected than we have realized? The search for answers continues. Pioneer anomaly. In the vastness of space, a spacecraft continues its journey, hurtling through the cosmos toward the outer edges of our solar system. This spacecraft is called Pioneer 10, and it was launched in 1972 as part of a groundbreaking mission to explore Jupiter. However, as Pioneer 10 traveled farther from Earth, scientists began to notice something unusual. Despite all calculations and expectations, the spacecraft was drifting slightly off course, subtle, yet undeniable. This unexpected deviation became known as the Pioneer anomaly. At first, the anomaly was thought to be the result of a simple error. Perhaps the spacecraft's thrusters were malfunctioning, or maybe there was a mistake in the original navigational calculations. But after repeatedly checking and confirming the data, it became clear that something far more mysterious was happening. Pioneer 10 appeared to be moving more slowly than predicted, and no known force could fully explain the discrepancy. Over time, scientists proposed several theories to account for the anomaly. The most widely accepted explanation involved heat being radiated from the spacecraft's onboard systems. This radiation could, in theory, create a small but measurable push in the opposite direction of travel. However, the mystery only deepened when Pioneer 11, a similar spacecraft launched a few years later, exhibited the same unexpected behavior. This raised new questions. Could there be an alternative explanation? Could something more profound be influencing these spacecraft? One possibility is the existence of an unknown force operating in the distant reaches of space, something not yet accounted for by current physics. Some scientists have even speculated that the Pioneer anomaly might be linked to dark matter or dark energy, the mysterious substances believed to make up most of the universe, but which remain largely undetectable. Though the Pioneer anomaly might seem like a minor irregularity in the vast expanse of space, it raises significant questions about the accuracy and completeness of our understanding of the universe. What is the source of this mysterious force? Could it point to a fundamental gap in our knowledge of physics? Might it one day lead to groundbreaking discoveries that transform how we view space and time? The answers, it seems, are still out there, waiting to be discovered. The flyby anomaly. When spacecraft fly past a planet, they often use the planet's gravity to gain speed and adjust their trajectory. This technique is known as a gravity assist. The concept is straightforward. The spacecraft receives a boost without using any extra fuel. However, Over the years, scientists have observed something unusual when analyzing data from these flybys. The spacecraft were not behaving exactly as expected. In many cases, they appeared to slow down slightly more than they should have. This puzzling behavior is known as the flyby anomaly. The mystery first came to light in the 1990s when the European Space Agency's Ulysses spacecraft and NASA's Galileo probe both experienced small, unexplained changes in their velocities during flybys. Initially, these discrepancies were thought to be minor errors, perhaps a glitch in the equipment or a miscalculation. But as more missions, including Rosetta and Cassini, also showed similar unexpected slowdowns, it became evident that something more significant was happening. The anomaly was perplexing. Spacecraft flying past planets should gain speed due to the planet's gravitational pull, not lose it. Scientists began ruling out potential explanations like radiation pressure, measurement errors, or atmospheric friction. Still, none of these accounted for the consistent pattern of unexplained deceleration. This led to deeper questions. Could an unknown force be at work? Is there a hidden factor subtly influencing the spacecraft's motion? One hypothesis suggests that spacecraft might be emitting small amounts of heat from their engines or materials, which could be enough to alter their paths slightly. However, this theory hasn't been definitively proven. The true cause of the flyby anomaly remains a mystery. Some wonder if it could indicate a deeper misunderstanding of gravity itself, or possibly hint at new physics waiting to be discovered. The flyby anomaly continues to intrigue scientists. It's a subtle but powerful reminder that, even after decades of space exploration, the universe still holds secrets that challenge our understanding of the fundamental laws of physics. Oumuamua's non-gravitational acceleration. Something extraordinary happened when a mysterious object zoomed through our solar system at a speed far greater than anything we had ever observed before. This object, named Oumuamua, was unlike any asteroid or comet we had encountered. What truly captured the attention of scientists was something even more bizarre. It appeared to be accelerating in a way that defied the usual laws of physics. Normally, objects traveling through space follow predictable paths, influenced solely by gravity. But Oumuamua's trajectory didn't quite match those expectations. As it passed by the sun, it sped up, but not in a manner that could be fully explained by gravity alone. Even more puzzling, there was no visible tail of gas or dust, which we would typically expect if it were a comet shedding material. It was as if something invisible was pushing it in a direction it shouldn't naturally go. This non-gravitational acceleration left scientists scratching their heads. Several theories emerged. Could the object have been propelled by solar radiation pressure? Was it releasing small amounts of gas in a way we couldn't detect? Or was there a completely unknown force at play? Something we hadn't even considered? Some researchers even speculated that Oumuamua might be an artificial object, perhaps a probe sent by an advanced alien civilization. While this idea remains highly speculative, it added fuel to the mystery. The object's unusual shape only deepened the intrigue. Unlike most asteroids, which tend to be roughly spherical or irregular, Oumuamua was cigar-shaped. This raised further questions. Could it be a fragment of something much larger? Or is its strange motion evidence of an entirely new class of cosmic phenomenon? Oumuamua's brief visit to our solar system opened up a wave of curiosity about the behavior of interstellar objects. While most of its secrets remain locked away, its journey reminds us that the universe is still full of mysteries waiting to be uncovered. Quantum biology phenomena. Imagine a world where the strange, invisible forces of quantum mechanics, the rules that govern the behavior of tiny particles, play a role in the very processes of life itself. This is the fascinating and mysterious realm of quantum biology, where the microscopic world of atoms and particles intersects with the biology of living organisms. Quantum mechanics reveals that particles can exist in multiple states at the same time. They can teleport between locations and even influence each other instantly, regardless of distance. These behaviors seem entirely disconnected from our everyday experiences. Yet, in recent years, scientists have uncovered compelling evidence suggesting that quantum phenomena may be occurring in biological systems in ways once believed impossible. One of the most intriguing mysteries in quantum biology is the potential role of quantum coherence in processes like photosynthesis. When plants absorb sunlight, they convert it into energy with remarkable efficiency, far surpassing that of any man-made solar panel. Some researchers believe that molecules within the plant may be using quantum coherence to transfer energy more effectively, allowing it to move through the system in a way classical physics cannot fully explain. It's as though the plant is tapping into quantum effects to boost its energy conversion, a concept that challenges conventional biological understanding. Another area where quantum mechanics might be at play is in animal navigation. For instance, migrating birds may use a phenomenon known as quantum entanglement to detect the Earth's magnetic field, enabling them to navigate across vast distances with stunning accuracy. If this is true, it would suggest that our understanding of both biology and physics is far more interconnected than previously imagined. The mystery of quantum biology remains largely unsolved. Could the bizarre rules of quantum mechanics be influencing life in ways we are only beginning to understand? As scientists continue to explore this enigmatic field, their discoveries may unlock a completely new way of understanding life itself, one that blends biology with the strange and wonderful world of quantum physics. Sure, here's a rewritten version of your text with complete sentences and improved clarity. Quantum consciousness interaction. What if the very act of thinking, the consciousness behind your thoughts, is somehow connected to the strange and mysterious world of quantum mechanics? It's a mind-bending idea that has intrigued both scientists and philosophers for decades. This concept is known as the theory of quantum consciousness interaction. At first glance, the brain appears to function like a classical system, governed by well-understood biological processes. However, some scientists have proposed that quantum mechanics might actually play a fundamental role in the nature of consciousness itself. Quantum mechanics, with its bizarre and counterintuitive rules, describes a reality where particles can exist in multiple states at once and influence each other instantly, even across vast distances. Could these strange properties be influencing how our minds work? The theory gained significant attention through the work of physicist Roger Penrose and anesthesiologist Stuart Hameroff. They proposed that quantum processes might occur within the brain's neurons, specifically in structures called microtubules. These are tiny components inside cells that help maintain their structure and function. According to their theory, quantum effects within microtubules could help explain how the brain processes information, generates thoughts, and produces self-awareness. What makes this idea even more mysterious is the challenge of how quantum states could exist in the brain's warm, wet, and noisy environment. Normally, quantum effects only occur in highly controlled, isolated systems, typically in laboratory conditions. Yet, if quantum mechanics truly influences consciousness, it could revolutionize our understanding of the mind. The mystery continues. If consciousness is indeed connected to quantum mechanics, what does that mean for our understanding of reality itself? Could quantum physics hold the key to unlocking the deepest secrets of the human mind? Or are we simply projecting quantum phenomena onto processes that are entirely classical in nature? As research into quantum consciousness continues, we may one day discover that the connection between mind and matter is far more mysterious and more fundamental than we ever imagined. Quantum retrocausality. Quantum retrocausality is an eerie and perplexing concept in physics that challenges our traditional understanding of time. In the realm of quantum mechanics, particles do not adhere to the straightforward rules of cause and effect that we experience in everyday life. Instead, They behave in ways that seem unpredictable, existing in multiple states at once or appearing to be influenced by events that have not yet occurred. This is where the concept of retrocausality enters the picture. In some interpretations of quantum mechanics, it is proposed that actions taken in the future can influence events in the past. This suggests that time may not flow in a single, linear direction like an arrow. Instead, time could be more fluid, with cause and effect occasionally operating in reverse. One of the most well-known experiments that touches on this idea is the double-slit experiment. In this experiment, particles such as electrons behave differently depending on whether or not they are being observed. If quantum retrocausality is real, then the act of observing a particle in the future could influence how it behaved in the past, before the observation even took place. This is a strange and unsettling idea. If the future can affect the past, then time itself might not be as linear or as stable as we once believed. Could our entire understanding of causality be fundamentally flawed? Is it possible to design an experiment that could definitively test whether retrocausality is real, or is it destined to remain a theoretical curiosity? Quantum retrocausality forces us to rethink not only the nature of time, but also the very fabric of reality. If time can loop or twist in this way, the mysteries of the universe might run far deeper than we have ever imagined. And the truth, it seems, could be waiting for us in the strange and elusive quantum realm, just beyond our current grasp. Quantum immortality. What if death isn't truly the end? What if a part of us continues to exist, branching into a new reality? This unsettling yet fascinating idea lies at the heart of quantum immortality, a concept that stretches our understanding of life, death, and the very fabric of the universe. Quantum immortality is rooted in the strange and mysterious realm of quantum mechanics. In this field of physics, particles can exist in multiple states at once, and their specific outcomes are only determined when observed. This idea gives rise to the many-worlds interpretation, which suggests that for every possible outcome of an event, a new universe is created. In essence, every choice we make and every random event that occurs causes reality to branch into countless parallel universes, each with a different outcome. Now, consider a life-threatening situation, such as a fatal accident. According to the theory of quantum immortality, when faced with death, your consciousness does not simply cease to exist. Instead, in the framework of many worlds, a version of you survives in a parallel universe where the fatal event never happened. From your point of view, you continue to live, although you may have unknowingly transitioned into another version of yourself in a different universe where you survived. The mystery of quantum immortality lies in how it challenges everything we think we know about life and death. If we truly live in a multiverse, could we be shifting from one reality to another without ever realizing it? If every near-death experience is actually a transition to a different universe, does death really exist? Or is it merely a passage into an alternate version of reality? While quantum immortality remains a highly speculative and unproven idea, it sparks deep and eerie questions about the nature of our existence. Is death truly the end, or could we, in some form, continue to live across infinite realities? The answer remains one of the most intriguing and unresolved mysteries in quantum physics. Quantum suicide. Quantum suicide is a mind-bending concept rooted in the strange rules of quantum mechanics. It suggests a scenario where death is something you could, in theory, survive, depending on your perspective. At the core of quantum suicide lies the many-worlds interpretation of quantum mechanics. This theory proposes that every time a decision is made or a random event occurs, the universe splits into multiple branches. In each branch, a different outcome happens. For example, if you flip a coin, one version of you sees heads and another sees tails, each in a separate, parallel universe. Now, imagine you're in a life or death situation, a gun pointed at your head, and the trigger is pulled. According to the idea of quantum suicide, instead of simply dying, the universe splits at that moment. In one universe, you die. In another, you survive. From your perspective, you would always experience the outcome where you survive. You would never be aware of the version where you died because your consciousness continues in the universe where you're still alive. It's as if your awareness jumps into the branch of the universe where the fatal event never happened. The unsettling mystery here isn't just the idea that death could be sidestepped. It's the deeper question: does consciousness always follow the path of survival? If every life or death moment leads to a split in the universe, does your experience always continue in the branch where you live, while the versions where you don't are essentially lost to you? This idea raises profound philosophical and scientific questions about the nature of life, death, and consciousness. It challenges our understanding of reality and suggests that death may simply be another outcome in the multiverse, one that we might never experience firsthand. Though purely theoretical, quantum suicide remains one of the most chilling and fascinating ideas in modern physics. Quantum Zeno effect. Have you ever noticed that when you stare at a clock, the second hand seems to stop moving? You blink, and it's as if time itself has paused, frozen in place. This strange sensation mirrors a real and fascinating phenomenon in quantum mechanics known as the quantum Zeno effect. In our everyday lives, we experience time as a continuous, smooth flow. But in the quantum world, things behave very differently. Quantum particles can exist in multiple states simultaneously until they are observed. However, the quantum Zeno effect turns this idea on its head. It suggests that if you observe a quantum system frequently enough, you can actually prevent it from evolving or changing at all. Imagine a particle, like a radioactive atom, that has a 50-50 chance of decaying over a given period. Normally, it would eventually decay on its own. But in the quantum realm, if you continuously measure the particle, you can stop this decay process. The act of constant observation effectively freezes the particle in its current state. The more often you check on it, the less likely it is to change, as if you were trapping it in time. Though it sounds like science fiction, this effect has been demonstrated in real-world experiments involving atoms and photons. What's even more intriguing is the possibility that the quantum Zeno effect could extend beyond tiny particles. It raises the question: could observation itself have a profound impact on the very nature of reality? This leads to a deeper mystery. Could there be a connection between consciousness and the quantum world? If continuous observation can pause the progression of time, what does that say about the nature of time, reality, and the universe itself? The quantum Zeno effect leaves us with a profound and unsettling thought. Is reality as fluid and dynamic as it appears, or can it truly be frozen by the mere act of watching? Quantum spin liquids. Quantum spin liquids do not behave the way we typically expect atoms and electrons, the fundamental building blocks of matter, to behave. These particles follow rules that often seem strange and defy common sense. One of the most puzzling phenomena in this realm is the concept of quantum spin liquids, an unusual and exotic state of matter that challenges everything we think we know about particle behavior. Normally, when particles like electrons interact, they tend to align in predictable ways. This alignment leads to the formation of solids or liquids with a well-defined structure. However, in a quantum spin liquid, the behavior is dramatically different. Although the particles are in a solid-like arrangement, they act as if they are in perpetual motion, never settling into a fixed, stable configuration. Instead of their spins, a fundamental property of particles, pointing in a fixed direction, the spins in a quantum spin liquid continuously flip and fluctuate. Remarkably, this happens even at absolute zero temperature, where all motion is typically expected to cease. The idea of quantum spin liquids was first proposed in the 1970s. Only recently, though, have scientists begun to find experimental evidence suggesting that these states might truly exist. Certain materials, such as copper oxide compounds, have shown signs of this unusual spin behavior that cannot be explained by classical physics alone. What makes quantum spin liquids particularly exciting is their potential for future technologies. They may play a key role in the development of quantum computing, where information is stored in quantum states rather than traditional bits. These materials might also offer new ways to manipulate magnetic fields, opening doors to innovations we've yet to fully imagine. However, there's a significant challenge. Quantum spin liquids are incredibly difficult to observe and study. Much of their nature remains cloaked in mystery. Are these quantum spin liquids the key to unlocking entirely new states of matter? Or are we merely glimpsing the surface of a far deeper quantum reality? This strange, ever-moving state of matter could ultimately help us understand the fundamental forces of nature in ways we've never considered before, even influencing our understanding of time itself. Some researchers are now exploring whether time might emerge from quantum entanglement, suggesting that our most basic concepts could be rooted in the same strange physics that governs quantum spin liquids. The emergence of time from quantum entanglement. We experience time every day, yet we understand so little about it. We watch the seconds tick by, yet when we venture into the realm of quantum mechanics, time becomes far less certain. In fact, there is a fascinating mystery unfolding at the intersection of quantum entanglement and the emergence of time itself. At the core of quantum mechanics lies the concept of entanglement. This phenomenon occurs when particles become entangled, meaning their states are linked in such a way that the behavior of one particle affects the behavior of another, regardless of the distance between them. It's a bizarre connection, one that seems to transcend the normal boundaries of space and time. But here's the mystery. If time is something we experience as a constant, linear flow, how does it emerge from the strange and seemingly disconnected world of quantum mechanics? Some physicists have proposed that time might not be fundamental at all. Instead, they suggest that time could emerge from quantum entanglement itself, a process where the interconnectedness of particles somehow gives rise to the flow of time as we perceive it. Essentially, instead of time being a background feature of the universe, it could be a product of how quantum particles interact. This raises a haunting question. If time is a result of quantum interactions, what does that mean for our everyday experience? Could time, as we know it, be an illusion created by the entanglement of particles? And if time can emerge in such a way, does this imply that in the earliest moments of the universe, before the first particles even formed, time itself might not have existed? This mystery is far from solved, but it challenges everything we think we know about time. As scientists continue to explore the quantum realm, we may uncover that time is far more mysterious and far more deeply connected to quantum mechanics than we ever imagined. The answer to this question could profoundly alter the way we understand the universe itself. Negative mass effect. In the strange world of physics, there is a concept of mass that behaves in a way we don't expect: negative mass. Imagine an object that, instead of being pulled toward the ground like we would expect, actually repels it. This concept forms the core of the mysterious idea of negative mass. In the universe as we understand it, mass is always positive. Objects with mass, whether they are planets, cars, or even atoms, are attracted to one another through gravity. The larger the mass, the stronger the gravitational pull. But what if there existed a form of mass that acted in the opposite way? What if it had a negative value, causing it to move in a completely counterintuitive direction? Negative mass would defy everything we know about physics. If you pushed an object with negative mass, instead of it moving in the direction you pushed, it would accelerate toward you, as if being pulled by the force you applied. This would create a bizarre and almost eerie effect, as though the laws of motion were being turned inside out. While scientists have never observed negative mass in the real world, it isn't entirely out of the question. Theoretically, certain exotic particles or conditions in the universe might give rise to negative mass. Some physicists even speculate that dark energy, the mysterious force responsible for the accelerated expansion of the universe, might be related to negative mass. The concept of negative mass challenges the very foundation of our understanding of gravity, motion, and the nature of the universe. Could it exist in some hidden corner of the cosmos, or is it simply a strange mathematical curiosity? The idea leaves us wondering. If we ever discovered it, would we be able to harness its power, or would it completely rewrite the rules of physics as we know them? The delayed choice quantum eraser is a thought-provoking experiment that challenges our conventional understanding of time and causality. It explores the intriguing idea that the way we observe the universe could potentially affect the past, a notion that initially seems impossible. However, the experiment suggests that in the quantum world, observation might not only impact the present, but could also influence events that have already occurred. To understand this, consider the well-known double-slit experiment. In this experiment, a particle such as a photon is sent through two slits, and it behaves like a wave, creating an interference pattern on a screen behind it. This pattern is similar to how water waves overlap and form ripples. However, the situation becomes peculiar when you attempt to observe which slit the photon passes through. In this case, the photon behaves like a particle instead of a wave, and the interference pattern disappears. This observation seems to alter the behavior of the photon, even though the measurement is taken after the photon has passed through the slits. This raises a significant question. How can the act of observation influence the particle's behavior after it has already passed through the slits? The delayed choice quantum eraser builds on this concept and goes even further. In this experiment, scientists set up a system where, after the photon has passed through the slits, they have the option to either observe or erase information about its path. The eerie part of the experiment is that the decision to erase or observe this information, made after the photon has already passed through the slits, seems to retroactively influence the interference pattern the photon creates. It's as if the photon decides whether to act as a wave or a particle depending on the later decision to observe or erase the information. This creates a paradox. If the future can affect the past, how do we truly understand causality? Does the act of observation create reality, or does it merely reveal something that already exists? The delayed choice quantum eraser forces us to reconsider our understanding of time, space, and the nature of reality itself, suggesting that the universe is far more mysterious and flexible than we ever imagined. Non-locality without entanglement. In the perplexing realm of quantum physics, particles appear to defy the conventional rules of reality. They can exist in multiple locations simultaneously and, astonishingly, communicate with one another instantaneously, regardless of the vast distances that separate them. This strange phenomenon is known as quantum entanglement, one of the most mind-bending aspects of quantum theory. But what if particles could be connected across space without the need for entanglement? This introduces an even more mysterious concept, non-locality without entanglement. In the quantum world, non-locality refers to the idea that particles can influence each other instantly, no matter how far apart they are. When two particles are entangled, measuring one affects the state of the other, regardless of the distance between them. This has been confirmed through numerous experiments, establishing a seemingly spooky connection between distant particles. However, in some experiments, physicists have observed that this instantaneous influence can occur even when the particles are not entangled at all. This discovery challenges our foundational understanding of space and time. If particles can interact over great distances without being entangled, how is this possible? How do particles know what the other is doing without any visible link between them? Some scientists propose that there may be a deeper, hidden connection between particles, something that goes beyond our current understanding of entanglement and quantum fields. The mystery of non-locality without entanglement does more than question the way particles interact. It compels us to rethink the very fabric of reality itself. Could the universe be interconnected in ways that don't adhere to the traditional rules of physics? As researchers continue to explore this enigmatic phenomenon, they may uncover secrets about the true nature of space, time, and the universe, secrets that are even stranger than we could have ever imagined. Tachyons, faster than light particles. Imagine a particle that can travel faster than the speed of light, a concept that defies everything we currently understand about the universe. Welcome to the strange and mysterious world of tachyons. These are hypothetical particles that, if they exist, could completely upend our understanding of physics. According to Einstein's theory of special relativity, nothing can exceed the speed of light. It's a fundamental law that has held up under rigorous testing and observation. However, tachyons are theoretical particles that challenge this rule. Some physicists suggest that tachyons would possess imaginary mass, which would allow them to move faster than light. But if that's true, they would behave in ways that are completely unnatural according to the laws of physics as we currently know them. One of the biggest mysteries surrounding tachyons is the fact that they have never been observed. No one has ever detected a tachyon directly, but they do appear in certain mathematical equations used in theoretical physics. Some scientists believe that if tachyons are real, they could help explain several unexplained phenomena in the universe. For instance, could tachyons be related to dark matter, the invisible substance that makes up most of the universe's mass? Or might they be tied to the strange behaviors seen in quantum mechanics, or even to the very nature of space-time itself? Another fascinating, though unsettling, possibility is that tachyons might offer insights into time travel. If these particles can move faster than light, could they also move backward in time? Could they create time paradoxes or even allow for the alteration of past events? Despite the lack of experimental evidence, tachyons remain a captivating subject in theoretical physics. Could they exist somewhere in a hidden corner of the universe, waiting to be discovered? Or are they merely a mathematical curiosity, a puzzle that may never be solved? Either way, the mystery of tachyons continues to intrigue scientists and push the boundaries of what we believe is possible, leaving us to wonder, are the laws of physics more flexible than we ever imagined? Closed time-like curves. Time travel has long been a subject of fascination and mystery. But what if time itself was more flexible than we ever imagined? What if there were actual paths in the fabric of space-time that could loop back on themselves, allowing someone to travel into their own past? This eerie and mind-bending concept is known as closed time-like curves, or CTCs, and it could unlock secrets that challenge everything we believe about time and causality. According to Einstein's theory of general relativity, space and time are not separate entities, but are intricately woven together into what we call space-time. This fabric can be warped and curved by the presence of mass and energy, particularly under extreme conditions. Near a black hole, or around a rapidly rotating massive object, this curvature could, in theory, be so intense that time itself bends into a loop. Imagine drawing a circle, not in space, but in time. You begin at one moment, and by following the curve, you eventually arrive back at the same moment in the past. In other words, you return to a point you have already experienced. This is the essence of a closed time-like curve. What makes CTCs so strange and so intriguing is that they allow for the theoretical possibility of time travel. If such loops truly exist, they could let someone revisit past moments, perhaps even change past decisions. But this raises many difficult questions. Could such time loops make time travel possible, or would they lead to paradoxes that defy logic and physics? One of the most famous paradoxes is the grandfather paradox. in which someone travels back in time and prevents their own ancestor from existing, thereby preventing their own birth. If CTCs are real, could scenarios like this actually happen? Or would the universe somehow prevent paradoxes through mechanisms we don't yet understand? Some theorists have even speculated that closed timeline curves might provide a kind of bridge to other timelines or alternate dimensions, realities that may exist alongside our own, but remain inaccessible through conventional means. While closed timeline curves remain purely theoretical for now, their implications are profound. They represent one of the most captivating mysteries in modern physics. What if time is not a straight line as we perceive it, but instead a loop, capable of twisting, turning, and perhaps even breaking? As scientists continue to explore the possibilities, the search for answers persists. And the deeper we look, the more mysterious time becomes. Non-locality without entanglement. In the strange and fascinating world of quantum physics, particles often appear to defy the rules of classical logic. They can exist in multiple states or locations at once, and they can seemingly communicate instantaneously across vast distances. This puzzling behavior is best known through the phenomenon of quantum entanglement, one of the most mind-bending aspects of quantum theory. Quantum entanglement occurs when two or more particles become linked in such a way that the state of one particle directly affects the state of the other, no matter how far apart they are. This phenomenon has been observed and confirmed through numerous experiments, suggesting a spooky connection between distant particles, as Albert Einstein once described it. However, an even more mysterious idea has emerged in recent years: non-locality without entanglement. In quantum mechanics, non-locality refers to the idea that particles can influence one another instantaneously across space. Traditionally, this has been explained through entanglement. But in certain experiments, physicists have observed signs that particles might affect each other without being entangled at all. This discovery challenges our fundamental understanding of space, time, and causality. If particles can interact across distances without any entanglement, how do they do it? How can one particle know what another is doing without any direct or known connection? Some scientists theorize that there may be a deeper, hidden layer of reality that connects particles, something beyond the current concepts of entanglement and quantum fields. The phenomenon of non-locality without entanglement doesn't just raise questions about how particles interact. It forces us to reconsider the very structure of the universe. Could it be that the universe is interconnected in ways that defy the established laws of physics? As researchers continue to explore this phenomenon, they may uncover profound truths about the nature of space, time, and reality itself. Truths that are far stranger than we ever imagined. Observer effect variations. The idea that simply observing something could change its behavior might sound like science fiction. However, in the strange and fascinating world of quantum mechanics, this is precisely what happens. This phenomenon is known as the observer effect, a mysterious concept suggesting that reality itself can be influenced by the mere act of observation. In the classic double-slit experiment, scientists fire particles such as electrons through two slits. When unobserved, these particles behave like waves, creating an interference pattern on the other side. But when the particles are observed, measured, or even just checked, their behavior changes. Instead of acting like waves, they behave like particles, and the interference pattern disappears. It appears as though the act of observing them causes the particles to decide how to behave. But here's where it gets even more intriguing. This shift in behavior doesn't always happen in the same way. The mystery deepens when we explore the variations in the observer effect. In some experiments, it's clear that observing a particle changes its state. In others, the change is subtle or doesn't occur at all. This raises a compelling question. Why do some observations seem to collapse the wave function, while others have little to no noticeable effect? Could there be unknown factors influencing when and how observation alters quantum systems? Some physicists believe the observer effect reveals profound truths about the relationship between consciousness and reality. Others argue it's merely an artifact of our methods of measurement. Is it possible that our understanding of observation and measurement in quantum mechanics is still incomplete? Or is there something deeper happening? Perhaps an unseen connection between the observer and the observed? These variations in the observer effect continue to baffle scientists, leaving us with more questions than answers. How much does our perception truly shape reality? Could the simple act of observation itself be altering the very fabric of existence? The answer remains hidden, for now, waiting to be discovered. Quantum Cheshire Cat. Imagine watching a cat in a box. You look away for a moment, and when you look back, you find the cat's tail in one place and its head in another. It sounds impossible, but this is essentially what physicists refer to as the quantum Cheshire Cat, a bizarre and mind-bending concept from the world of quantum mechanics. The quantum Cheshire Cat is an idea that emerged from a strange experiment designed to explore how quantum particles behave. In the experiment, researchers sent particles like photons through a device that could split them into different parts. What they discovered was eerie. In a quantum system, a particle and its properties, such as its spin or polarization, can become separated. In other words, the photon's body could travel one path, while its properties, like spin, would take another. This is strikingly similar to the Cheshire Cat from Alice in Wonderland, where the cat's body could vanish, leaving only its grin behind. This phenomenon challenges our entire understanding of objects and their characteristics. In our everyday lives, we expect an object and its properties to be inseparable. If you see a cat, you expect its tail and head to be part of the same whole. But in the quantum world, particles can exhibit this strange disconnection. This raises profound questions. If particles and their properties can be separated, how do we truly understand the nature of reality? What does this tell us about the relationship between an object and its attributes? The quantum Cheshire Cat doesn't just challenge our understanding of particles. It forces us to reconsider how deeply connected reality really is. It makes us wonder whether our perception of the world is as coherent as we believe. In the end, this mystery hints at the strange and hidden nature of the quantum realm. Could the universe be less solid and less predictable than we've ever imagined? Beneath the calm surface, could there be a storm of quantum foam? Quantum foam. Beneath the seemingly smooth and predictable fabric of space and time lies a mysterious and chaotic realm, one so small that none of our current instruments can detect it. This is the world of quantum foam. Quantum foam is a bizarre and almost eerie concept in physics that challenges everything we think we know about the nature of reality. It is believed to exist at the Planck scale, which is the smallest possible scale of space and time. At this incredibly tiny scale, space is anything but empty. Instead, it constantly fluctuates, bubbles, and shifts in a wild, unpredictable manner. Imagine the surface of a calm ocean. Now, instead of gentle waves, picture a sea of rapid, chaotic ripples and froth. This is what quantum foam is like. It consists of minuscule fluctuations that appear and vanish within fractions of a second, far smaller than even atoms. These fleeting disturbances are what scientists refer to as quantum foam. The mystery of quantum foam lies in how it fits into our broader understanding of the universe. At larger scales, space appears smooth and orderly. But at the quantum level, it is alive with activity. Particles constantly pop in and out of existence in a jittery, unpredictable dance. Although these fluctuations are so tiny that they cannot be directly observed, they may have a profound effect on how space-time behaves. They could influence everything from the nature of gravity to the fundamental forces that govern the cosmos. Quantum foam may also offer crucial insights into the origins of black holes and the Big Bang. Some physicists theorize that the extreme density and heat present at the beginning of the universe were shaped by quantum foam, laying the groundwork for the cosmos to unfold. However, exactly how these microscopic fluctuations could give rise to the vast universe we see today remains one of physics' greatest unanswered questions. The concept of quantum foam is one of the most mind-bending ideas in modern science. It suggests that beneath the calm and orderly surface of reality, space itself may be far more chaotic and unpredictable than we ever imagined. And as scientists continue to investigate this strange and hidden realm, the mysteries of the universe only seem to grow deeper. The measurement problem. The measurement problem is a baffling mystery that has puzzled scientists for decades. It is considered one of the most fundamental questions in physics. At its core, the mystery is deceptively simple. How do we transition from the strange, blurry world of quantum particles to the clear and predictable reality we experience in everyday life? In the quantum realm, particles such as electrons and photons do not have definite positions or speeds. Instead, they exist in a state of probability, meaning they can be in many places at once or possess a range of possible speeds. This state continues until we measure them. Only when we observe or measure a particle does it choose a specific state. This moment is known as wave function collapse. But this leads to a profound problem. Why does the mere act of observing or measuring a particle force it into one defined state, when previously it existed in many possible ones? This puzzling transition presents a strange paradox. On one hand, quantum mechanics reliably predicts particle behavior with astonishing precision. On the other hand, it offers no clear explanation for why or how measurement alters that behavior so dramatically. How can something so uncertain, something that exists in multiple potential states, suddenly become definite just because we looked at it? This is the essence of the measurement problem. It raises deeper questions about the very nature of reality. Does observing the universe actually create the reality we experience? Or is there a hidden layer of physics that we have yet to discover? Some theorists propose that consciousness itself might influence quantum outcomes, while others believe there are still unseen physical laws at play. Although the measurement problem may seem abstract, it lies at the heart of our understanding of the universe. It challenges our assumptions about what is real and opens the door to mysteries that could one day unveil the true nature of the cosmos. Scale relativity. Everything in the universe is connected by scale, from the tiniest particles within an atom to the vast galaxies spread across the cosmos. The laws of physics do not operate the same way at every level. They can change depending on the scale being observed. But what if our entire understanding of space, time, and even the fabric of reality itself also shifts with scale? This is the mysterious concept at the heart of scale relativity. Scale relativity is built on a profound question. Do the same laws of physics apply regardless of how small or large a system is? In our everyday experience, the world seems to follow predictable rules. Gravity pulls objects downward. Things move in direct, consistent ways. However, at the quantum level, these rules begin to fall apart. Particles behave in strange, unpredictable ways, sometimes even existing in multiple states at once. So what happens when we consider the universe at all scales, from subatomic particles and atoms to entire galaxies? Scale relativity suggests that just as Einstein's theory of relativity showed us that space and time are flexible and can be curved by gravity on large scales, there may be similar shifts at much smaller scales as well. It proposes that the principles which govern the very large might also apply to the very small, though their effects may look quite different. In essence, the rules of the universe may not be fixed. Instead, they could change depending on the scale at which they are observed, creating a more dynamic and unpredictable version of reality than we've previously imagined. One of the most fascinating aspects of scale relativity is its potential to bridge the gap between quantum mechanics and general relativity, the two foundational theories of modern physics that have never been fully unified. Could scale relativity be the key to connecting our understanding of the smallest particles with the behavior of the largest cosmic structures? The idea remains a compelling mystery, challenging scientists to rethink how the laws of physics work across all scales. The answers may one day unlock deeper truths about the nature of the universe and reality itself, possibly even revealing how virtual particles might become real. Virtual particles becoming real. In the strange and fascinating world of quantum physics, there exists a phenomenon that seems to challenge our very understanding of reality: virtual particles. These are incredibly small, short-lived particles that appear for only the briefest moment before vanishing without a trace. But here's where the mystery deepens. Could these virtual particles somehow become real? Virtual particles cannot be observed directly. They emerge from quantum fields, momentarily borrowing energy from their surroundings before fading away. According to quantum theory, they exist in a state of constant fluctuation, like tiny bubbles briefly forming and disappearing in the vacuum of space. Under normal circumstances, virtual particles are harmless and fleeting. They don't stick around long enough to create noticeable effects on a larger scale. But what happens if, for some reason, these ephemeral particles persist longer than expected? Could they actually transform into real particles, leaving lasting effects on the physical world? This question becomes even more intriguing when we consider phenomena such as the Casimir effect. In this effect, virtual particles seem to create a measurable force between two closely placed objects, as though these invisible entities are exerting a pull. Despite their transient nature, their presence produces a very real outcome, suggesting they might be more than just mathematical artifacts. Some theoretical physicists even propose that virtual particles could play a crucial role in the formation of new particles, especially in high-energy environments like those produced in particle accelerators. Under such conditions, virtual particles might absorb enough energy to break free from their quantum constraints and manifest as real, observable matter. This process could potentially lead to the creation of entirely new particles. If virtual particles truly have the potential to become real, it forces us to confront a profound question. Is the line between possibility and impossibility in the quantum world far more blurred than we ever imagined? Could the very boundaries of reality be more fluid and flexible than previously thought? The mystery of virtual particles turning real invites us to rethink the nature of existence itself. It challenges us to delve deeper into the hidden layers of the universe and explore the fundamental forces and interactions that shape the cosmos. Biometric gravity. The universe has puzzled scientists for centuries. While we understand how it works on large scales, such as with planets and galaxies, gravity remains elusive at the smallest scales governed by quantum mechanics. In this strange world of particles and fields, gravity doesn't quite fit in. This is where biometric gravity enters the picture, a fascinating idea that could help solve some of the biggest cosmic puzzles. In Einstein's theory of general relativity, gravity is described as the bending of space-time caused by mass and energy. This framework works incredibly well for massive objects like stars and black holes. However, at the quantum level, gravity behaves differently. It's as if something is missing, some vital piece of the puzzle that prevents us from fully explaining how the universe works at all scales. Biometric gravity offers a possible solution. What if there isn't just one kind of space-time in the universe, but two? In this theory, there are two distinct metrics, or ways of measuring space-time, that interact with each other. One metric governs the familiar large-scale gravitational effects we observe with planets and galaxies. The second could control the bizarre, unpredictable behavior of the quantum realm. What makes this idea especially compelling is its potential to bridge the gap between the two most powerful and currently incompatible theories in physics: general relativity and quantum mechanics. These two frameworks have never seamlessly aligned, but biometric gravity might be the key to finally unifying them. This raises an intriguing question. Could the existence of two separate space-time metrics explain phenomena we still don't fully understand, such as dark matter or the strange properties of black holes? If biometric gravity proves to be correct, it could completely transform our understanding of the cosmos, revealing how space-time behaves on both the largest and smallest scales. Ultimately, biometric gravity might be the breakthrough needed to connect the dots in one of the most profound mysteries of all: how the universe truly works. Einstein-Cartan theory. The groundbreaking idea that gravity results from massive objects bending space and time lies at the heart of Einstein's general relativity. But what if there is more to gravity than even Einstein envisioned? What if the very fabric of space-time can be influenced by something beyond just mass? This is where the Einstein-Cartan theory comes into play, a fascinating extension of Einstein's work that could provide new insights into some of the universe's deepest mysteries. Developed in the 20th century, the Einstein-Cartan theory builds upon general relativity by introducing a new concept: the influence of spin, an intrinsic property of particles, on spacetime. In this theory, gravity is not solely the result of mass curving spacetime. It is also shaped by the spin of particles as they move through it. This subtle yet profound addition may help explain certain puzzling phenomena in the universe. One of the most compelling aspects of the Einstein-Cartan theory is its potential to describe the behavior of matter under extreme conditions, such as within black holes or during the early moments of the Big Bang, where conventional physics breaks down. By incorporating spin into the very fabric of spacetime, the theory may offer a more complete understanding of gravity in these mysterious environments. But the intrigue doesn't end there. The Einstein-Cartan theory also introduces the concept of torsion, a twisting of spacetime caused by particle spin. This torsion could play a crucial role in the structure of the universe. Could this twisting force help explain the elusive nature of dark matter? Might it even hint at the existence of extra dimensions we have yet to detect? While the Einstein-Cartan theory may not be the final word on the nature of gravity, it opens the door to exciting possibilities. It raises a haunting question. What if the universe operates according to principles deeper than we've ever imagined, guided by forces and dimensions we are only beginning to uncover? Though still under investigation, the true potential of the Einstein-Cartan theory remains one of the most tantalizing mysteries at the forefront of modern physics. Double special relativity theory. Imagine a universe where the laws of physics change depending on your location or how fast you're moving. This is the world described by special relativity, the groundbreaking theory developed by Albert Einstein. According to this theory, time and space are not absolute. They are relative and depend on your speed. But what if there's more to the story? What if there isn't just one special framework for understanding space and time, but two? This idea lies at the heart of a fascinating concept known as double special relativity, DSR. At its core, DSR suggests that under extreme conditions, such as near black holes or during the early moments of the universe, not only is the speed of light a fundamental constant, but the quantum structure of space-time also becomes significant. While special relativity tells us that nothing can move faster than light, DSR goes further. It proposes that the structure of space-time itself might behave differently at incredibly small scales or at extremely high velocities. This means that the nature of the universe could be even more dynamic and flexible than we currently understand. What makes DSR especially compelling is how it challenges our existing views of space and time. In Einstein's theory, space and time are treated as one unified, consistent fabric. However, DSR suggests that at extremely high energies or speeds, space, and time might not behave in predictable ways. They could reveal hidden dimensions or properties we've yet to discover. Could DSR help us understand the behavior of particles moving near the speed of light? Might it provide clues about the mysterious forces of dark energy and dark matter? As scientists continue to investigate this bold theory, we are left with one profound question. What if the universe is far stranger and more layered than we ever imagined? Double special relativity pushes us to reconsider everything we thought we knew about space, time, and the fundamental nature of reality. The mass gap problem. In the strange and unpredictable world of quantum physics, there exists a perplexing mystery that has puzzled scientists for decades: the mass gap problem. Imagine a universe where particles are either extremely light, like photons, or incredibly heavy, like protons. But curiously, there seems to be a mysterious gap in between, a range where particles should exist but don't appear to. This unexplained absence challenges our understanding of the fundamental building blocks of matter. In particle physics, the Standard Model describes how particles interact through fundamental forces. It does a remarkable job explaining the behavior of both very light and very heavy particles. However, when we examine the mass range in between, particularly between the mass of a proton and heavier particles like the Higgs boson, we notice something strange. No stable particles seem to fit within this range. This is what physicists refer to as the mass gap. Why does this matter? Because understanding the mass gap could offer crucial insights into how the universe operates at its most fundamental level. Some theorists speculate that the solution to the mass gap may involve strongly interacting particles, particles bound tightly by one of nature's fundamental forces but which have never been observed. If such particles exist, they might hold the key to understanding deep and complex phenomena, including dark matter or the forces that shaped the early universe. The mass gap isn't just a technical curiosity. It could be a gateway to uncovering an entirely new layer of physical reality. Could this missing link reveal hidden particles or unknown forces? Might it change our understanding of everything, from the tiniest subatomic particles to the most powerful cosmic events? The mystery of the mass gap remains unsolved. But with every new discovery in quantum physics, we edge closer to revealing the secrets that may lie within, perhaps even secrets hidden in the nature of the Higgs boson itself. Higgs boson metastability. In 2012, physicists at CERN made a groundbreaking discovery: the Higgs boson, a fundamental particle responsible for giving mass to other particles. This discovery marked a monumental achievement in our understanding of the universe's basic structure. However, hidden within this breakthrough lies a fascinating and unsettling mystery: the concept of Higgs boson metastability. Metastability refers to a state that appears stable but is actually prone to change under the right conditions. Scientists theorize that the Higgs boson itself might exist in such a state. In simple terms, the Higgs field, which permeates all of space and is responsible for imparting mass, could be like a ball resting in a valley on a smooth landscape. In what we believe to be its current stable state, the ball is safely nestled in a shallow valley. But what if this valley isn't the lowest point? What if, someday, the ball could roll into a deeper, more stable valley, one that we haven't yet discovered or understood? This possibility is the essence of Higgs boson metastability. If the Higgs field were to transition into this deeper state, it could trigger a catastrophic chain reaction, fundamentally altering the laws of physics and the structure of the universe. While this may sound like science fiction, theoretical calculations suggest that such a scenario is, in principle, possible. Fortunately, if this shift were to occur, it would likely take billions of years, far beyond any current timescale of concern. Nonetheless, the real mystery remains. Are we living in a truly stable universe, or are we unknowingly perched on the edge of an unstable reality? Even though experiments have shown the Higgs boson to be stable for now, the potential for an underlying instability poses profound implications for the fate of the universe. This leads us to a haunting question. Is the universe as stable as we believe, or could we be just one step away from an unforeseen cosmic transformation? Future research, including experiments like those exploring dark matter and axions, may help us understand whether this lurking instability is real and what it could mean for the ultimate destiny of the cosmos. Axion dark matter experiment results. For many years, scientists have known that most of the universe's mass is not made up of ordinary matter, the kind we can see and touch. This mysterious, invisible substance is known as dark matter, and it accounts for about 85% of the total mass in the universe. However, the true nature of dark matter remains unknown. One of the leading theories proposes that dark matter could be composed of tiny, elusive particles known as axions. These particles have been extremely difficult to detect until recently. In a series of recent experiments, scientists have begun to gather promising evidence that brings us closer to identifying axions. These theoretical particles are believed to be incredibly light, stable, and weakly interacting, which could explain why dark matter has remained hidden from direct observation. Axions are also predicted to interact with electromagnetic fields, but only under very specific and rare conditions. The discovery of axions would be groundbreaking, offering a concrete explanation for dark matter and potentially revolutionizing our understanding of the universe. The mystery deepened when researchers received the results of a critical axion dark matter experiment. After months of analysis, they detected unexplained signals, subtle anomalies that could be connected to the behavior of axions. While these signals do not yet confirm the existence of axions, they are highly intriguing and suggest that we may be on the verge of uncovering a new realm of physics. The question now is, are these signals truly evidence of axions, or is another unknown phenomenon at play? Could this be the breakthrough that finally unravels the mystery of dark matter, or is there still more to uncover? As researchers continue to investigate, the axion dark matter experiment brings us one step closer to understanding the hidden forces that govern the universe. The search goes on. With it, the possibility of rewriting the very foundations of our understanding of reality. Chameleon particles. Imagine particles that can change their identity depending on where they are, almost as if they were hiding in plain sight. This is the strange and captivating idea behind chameleon particles, one of the most perplexing concepts in modern physics. Chameleon particles are theoretical entities named after the animal known for its ability to blend into its environment. Similarly, these particles are believed to change their properties based on their surroundings. In theory, they would interact more strongly in high-energy environments, but in low-energy regions, such as the vast emptiness of space, they would become nearly undetectable. This adaptive behavior makes chameleon particles incredibly elusive, which is why they remain so mysterious. The concept arose as part of an attempt to explain dark energy, the enigmatic force responsible for accelerating the expansion of the universe. Chameleon particles are hypothesized to be a potential explanation for dark energy because, like dark energy, their effects could vary depending on their location. In regions with a large concentration of mass, such as near galaxies or galaxy clusters, chameleon particles might interact more noticeably, offering potential insights into how the universe behaves on a large scale. However, in the near vacuum of space, where mass is minimal, these particles might essentially disappear, making them extraordinarily difficult to detect. If chameleon particles do exist, the implications would be profound. They could transform our understanding of space, energy, and gravity. They might even hold the key to explaining why the universe's expansion is accelerating. Despite significant scientific efforts, no one has yet been able to detect chameleon particles. Yet the very idea of them raises unsettling questions. Are there hidden forces all around us? Could there be particles constantly shifting their identity, just out of reach, waiting to reveal their secrets? Could these elusive chameleon particles be the missing link in the mystery of dark energy? Or are they simply a fascinating theory, still waiting to be uncovered? Grand Sasso faster-than-light neutrinos. In 2011, something extraordinary occurred deep underground in Italy. Scientists at the Gran Sasso Laboratory, working as part of the Opera experiment, observed an event that momentarily stunned the physics community. For a brief period, neutrinos, particles that are notoriously difficult to detect, appeared to be traveling faster than the speed of light. If this observation had been accurate, it would have shattered one of the most fundamental principles of physics, Einstein's theory of relativity, which asserts that nothing can move faster than light. Neutrinos are extremely small, nearly massless particles capable of passing through matter almost undisturbed. They are incredibly hard to study due to their elusive nature. However, this particular experiment suggested they were doing something far more astonishing than previously imagined. The team at Gran Sasso had sent a beam of neutrinos from CERN, located approximately 730 kilometers away. To their surprise, the neutrinos appeared to arrive slightly faster than light would have over the same distance. The implications were immense. If true, the results could upend everything we understand about space, time, and the fundamental limits of the universe. Scientists around the world scrambled to verify the findings. However, skepticism quickly emerged. Could this truly be a revolutionary discovery, or was it simply a mistake? After extensive investigations, researchers discovered an error in the timing equipment used in the experiment. Once this error was corrected, the anomaly disappeared, and the neutrinos were found to be traveling within the expected bounds of relativity. The mystery was resolved, or so it seemed. Although the faster-than-light neutrino phenomenon was ultimately attributed to a measurement error, the fact that such a result initially appeared plausible sparked deeper questions. It highlighted how fragile and incomplete our understanding of the universe might be. The Gran Sasso neutrino anomaly serves as a powerful reminder. Even a small observational anomaly can challenge the foundations of science and force us to re-examine what we think we know about the nature of reality. Neutrino flavor oscillation. Beneath the surface of our everyday experiences, a fascinating and mysterious phenomenon is unfolding: neutrino flavor oscillation. Neutrinos, tiny and nearly invisible particles, are engaging in a cosmic game of hide-and-seek that continues to baffle scientists around the world. This phenomenon is one of the most intriguing puzzles in particle physics and could be the key to understanding the fundamental nature of these elusive particles. Neutrinos come in three types, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. For a long time, scientists believed that once a neutrino was created in a specific flavor, it would remain that way permanently. However, in the late 1990s, that belief was upended. Researchers discovered compelling evidence that neutrinos can actually change, or oscillate, from one flavor to another as they travel through space. In other words, a neutrino that begins its journey as one type might transform into a completely different type along the way. This surprising discovery implied that neutrinos must have mass, something previously thought impossible for such minuscule particles. The realization that neutrinos have mass has had profound implications, reshaping our understanding of the universe and raising new questions in the fields of particle physics and cosmology. What makes this even more perplexing is that the mechanism behind these flavor oscillations remains largely a mystery. Scientists have been conducting experiments to track neutrinos over vast distances, such as those emitted from the sun or even from distant supernovae. Despite decades of research, we still don't fully understand how or why these oscillations occur. Could there be hidden forces at work that we haven't yet discovered? The mystery of neutrino flavor oscillation challenges much of what we thought we knew about the fundamental particles that compose our universe. The more we learn, the more complex the puzzle becomes. Could unraveling the secrets of neutrinos help us understand the origins of matter itself, or even the ultimate fate of the universe? The search for answers continues, and the mystery remains. Lorentz violation. Imagine a universe where the very fabric of space-time doesn't behave the way we've always believed it should. A world where the speed of light is no longer constant, and the fundamental rules that govern motion and interaction are subtly, but profoundly, different. This is the mystery of Lorentz violation. For over a century, Einstein's theory of special relativity has stood as a cornerstone of modern physics. One of its most critical principles is that the speed of light remains constant, regardless of the observer's position or motion. This idea is so deeply embedded in our understanding of reality that it underpins technologies like GPS and guides our concepts of space travel and cosmology. But what if this constant speed of light isn't truly constant after all? Lorentz violation suggests exactly that. It proposes that under certain extreme conditions, the laws of physics as we know them might break down, allowing the speed of light to vary depending on where you are in space-time. Could there be hidden forces or unknown physics operating at scales we've yet to explore? The mystery began when scientists observed small but intriguing anomalies in high-energy particles. These particles behaved in ways that didn't fully align with the predictions of relativity, suggesting that space-time itself might be subtly distorted and that light might travel at different speeds under specific conditions. To investigate these phenomena, researchers have focused on experiments involving cosmic rays and particles traveling at speeds approaching the speed of light, where signs of Lorentz violation are most likely to emerge. If Lorentz violation is real, it could unlock a deeper understanding of the universe. It might even offer a bridge between two seemingly incompatible realms of physics, quantum mechanics and general relativity. The implications are enormous. What if our current understanding of space-time is merely a shadow of a deeper, hidden reality, one that lies just beyond the limits of our perception? The search for answers continues, driven by the hope of uncovering new, hidden layers of the universe. Each anomaly, each unexplained observation, may be a clue pointing toward a more complete and unified picture of the cosmos. Muon anomaly, muon G2. In the tightly interwoven world of physics, one curious anomaly has captured the attention of scientists around the globe. This is the muon anomaly, also known as the muon G2 experiment. It might just be hinting at something much bigger, something that could challenge the very foundations of physics as we know them. Muons are subatomic particles similar to electrons. Think of them as heavier and unstable cousins of electrons. In 1961, scientists noticed something unusual about how muons behave in magnetic fields. According to the established laws of physics, the magnetic properties of muons should have aligned perfectly with theoretical predictions. However, when scientists measured how muons spin in a magnetic field, they observed a slight but persistent discrepancy. Something didn't quite add up. Fast forward to the 2000s, and experiments at facilities like Fermilab in Illinois began to investigate this anomaly more rigorously. Scientists carefully compared the behavior of muons with the predictions made by the Standard Model, the theoretical framework that describes how fundamental particles interact. To their surprise, the muons didn't behave as expected. They wobbled or wiggled in a way that didn't match the predictions. This discrepancy, this anomaly, suggests the existence of something beyond the Standard Model, a hidden force or undiscovered particle that we have yet to identify. The mystery becomes even more intriguing when you consider what this anomaly might imply. Could the muon anomaly be the first real sign of new physics? Could it reveal unknown particles or forces Some theorists propose that it might even be connected to dark matter or hint at extra dimensions of spacetime, concepts that have long remained in the realm of speculation. While the results of the muon G2 experiment have generated excitement across the scientific community, the mystery remains unsolved. Could this small difference in muon behavior lead to a revolutionary new understanding of the universe? The search continues, and with it, the tantalizing possibility of opening new chapters in our understanding of physics, including gravitational anomalies right here on Earth. Gravitational anomalies on Earth, the Hudson Bay mystery. On Earth, gravity is usually considered a constant force. It pulls us downward, keeps the oceans in place, and governs the movement of everything from falling apples to orbiting planets. However, in certain areas of our planet, gravity behaves in strange and unexpected ways. One of the most intriguing examples is known as the Hudson Bay anomaly. This anomaly, located in Canada near Hudson Bay, has puzzled scientists for decades. What makes it so unusual is that measurements of Earth's gravitational pull in this region are weaker than expected. In fact, gravity in this area is significantly lower than in the surrounding regions, almost as if something is missing beneath the Earth's surface. At first, scientists believed this phenomenon could be explained by a simple geological cause, such as a lack of dense rock in the area. However, as more data was collected over time, it became clear that the explanation might not be so straightforward. The Hudson Bay anomaly does not align neatly with any known geological patterns. One theory proposes that the anomaly is the result of ancient geological processes, possibly remnants from a time when the continent's structure was vastly different. Another possibility suggests that the anomaly is connected to mantle dynamics, the slow, complex movements within the Earth's interior over long geological timescales. Despite these theories, no definitive explanation has been found. What adds to the mystery is the speculation that the anomaly could be influenced by something even more exotic, dark matter. This mysterious, invisible substance is believed to make up a large portion of the universe's total mass. Could dark matter, with its elusive and largely unknown properties, be subtly affecting Earth's gravity in this region? The unexplained gravitational anomaly near Hudson Bay challenges our understanding of how gravity works and what forces are shaping our planet. Is there an unseen, hidden force at work beneath the surface? The mystery continues to unfold, leaving scientists with more questions than answers about the very fabric of our world. Have you ever heard the Earth hum? Earth's hum? Unexplained Earth oscillation. Have you ever heard a strange, low-frequency hum and wondered what could be causing it? You're not imagining things. For years, people around the world have reported hearing a continuous, eerie sound with no clear source. This phenomenon is known as the Earth's hum, or more formally, the unexplained Earth oscillation. Scientists are still working to understand what causes it. The hum is a low-frequency vibration, typically around 10 Hz. Most people can't consciously hear it, but some individuals report feeling it or hearing it faintly, especially in specific regions. It has been recorded in urban areas, remote locations, and even deep in the ocean. Strangely, the hum isn't always constant. It can come and go without any obvious pattern, adding to its mystery. Despite years of study, scientists have not been able to identify a definitive cause. One theory suggests that the hum is connected to tectonic activity, the movement of Earth's plates. Some researchers believe that small, undetectable seismic events might generate these vibrations. Others think atmospheric conditions, such as wind patterns or ocean waves, could be responsible, producing low-frequency sound waves that travel great distances. An even more curious idea is that human activity might be contributing to the hum. Industrial machinery, heavy traffic, or other man-made processes could be creating these vibrations. However, many of the clearest recordings of the hum have come from remote, quiet locations, places far from human interference. So what's really going on? Is the Earth singing, emitting vibrations we've never fully understood? Or is there some hidden, unseen force, natural or artificial, shaping these mysterious oscillations? The Earth's hum remains one of the most intriguing and unsettling mysteries of our planet, leaving us to wonder whether it's just a natural quirk or something far more profound, lurking beneath the surface. Ball lightning formation. During a lightning storm, a strange and glowing ball of light may suddenly appear, hovering in the air and moving erratically before vanishing just as mysteriously as it came. This phenomenon is known as ball lightning, one of the most elusive and puzzling occurrences in atmospheric science. Ball lightning has been reported for centuries, yet scientists still do not fully understand what causes it. Unlike regular lightning, which can be predicted, measured, and explained, ball lightning seems to defy the known laws of physics. These glowing orbs vary in size, ranging from that of a small ball to something as large as a basketball, and they can last anywhere from a few seconds to over a minute. Sometimes they float silently, while other times they move unpredictably, even passing through solid objects like windows. Witnesses often describe feelings of awe, confusion, and sometimes fear. The mystery begins with how these luminous balls are formed. Some theories suggest they result from electrical discharges during thunderstorms. However, what remains puzzling is how they are able to maintain their shape and motion without dissipating immediately. One popular hypothesis is that ball lightning is a form of plasma, a highly energized state of matter capable of conducting electricity. But the question remains, how does this plasma stay stable long enough to appear as a floating orb of light? Another theory involves interactions between lightning and materials in the environment, such as the Earth's magnetic field or unique chemical reactions that might occur in the atmosphere. Despite numerous scientific efforts, researchers have never been able to successfully recreate ball lightning under controlled laboratory conditions. As a result, the mystery of ball lightning remains unsolved. It raises the intriguing possibility that there are still hidden forces in nature we have yet to fully understand. Perhaps unlocking the secrets of this eerie phenomenon could lead to new insights into energy, electricity, and even the very fabric of space itself. Electromagnetic anomalies at Hessdalen Valley. In the remote Hessdalen Valley of Norway, something strange unfolds in the night sky. For decades, researchers have been investigating a phenomenon that defies conventional explanation. Mysterious glowing lights, known as the Hessdalen lights, appear regularly, often moving in ways that challenge our understanding of physics. These lights have puzzled both scientists and locals for over a century. Sometimes, they hover motionless as bright orbs, while at other times, they move erratically, darting across the sky as if guided by some unknown intelligence or pattern. Despite numerous studies and observations, no one has been able to determine the exact cause of these anomalies. One of the most prominent theories suggests that the lights are connected to electromagnetic phenomena. The unique geography of the Hessdalen region, including its proximity to certain mineral deposits, might create ideal conditions for unusual electromagnetic activity. Some scientists propose that ionized particles in the air, possibly influenced by the Earth's magnetic field or localized electrical charges, could be generating the lights. However, what continues to baffle experts is why this phenomenon occurs so consistently in Hessdalen, but not in similar regions around the world. The mystery deepens when more speculative ideas are considered. Could the lights be a manifestation of unknown forces, perhaps even related to dark energy or a yet undiscovered atmospheric phenomenon? Is it possible that they are tied to a hidden form of energy or reveal a different behavior of electromagnetic fields under specific conditions? The electromagnetic anomalies of Hessdalen Valley remain one of the most intriguing unsolved mysteries in modern science. As investigations continue, scientists are left with an unsettling possibility. What if these unexplained lights are merely the surface of a much deeper reality, an invisible force hiding in the very air around us? Spontaneous human combustion. Physics speculations. Spontaneous human combustion has terrified people for centuries. It refers to the mysterious and inexplicable phenomenon in which a person appears to suddenly burst into flames without any clear external ignition source. In many reported cases, the individual is found severely burned, sometimes reduced almost entirely to ashes, while the surroundings remain relatively untouched. But is this bizarre event even possible from a scientific standpoint? What does physics have to say about such occurrences? Although it may sound like something from a horror movie, there are real historical reports of spontaneous human combustion. Some theorists believe chemical reactions within the body could be responsible. One hypothesis suggests that a buildup of ketones, flammable chemicals produced during certain metabolic processes, might make the body more susceptible to ignition. If the concentration of these chemicals reaches a critical point, a small internal or external spark could potentially trigger a fire. Another commonly discussed explanation is the wick effect. According to this theory, a person's clothing could act like the wick of a candle, drawing melted body fat as fuel. This would allow a slow, intense burn that consumes the body without significantly affecting the surroundings. However, this doesn't fully explain why the ignition occurs in the first place, or why these fires sometimes burn for hours without spreading. Despite scientific attempts to understand these incidents, many questions remain unanswered. Why do some people reportedly combust while others do not? And why are such occurrences so incredibly rare? Could there be unknown physical forces or reactions at work? Phenomena we have yet to discover or understand. While spontaneous human combustion still lacks a definitive scientific explanation, it continues to fascinate and disturb. It reminds us that there are still countless mysteries surrounding the human body and the physical forces that govern it, waiting to be explored and understood. Sun's corona temperature anomaly. When we think of the sun, we often picture its bright, blazing surface, known as the photosphere, which glows at an intense temperature of around 5,500 degrees Celsius. However, what lies just above this surface has baffled scientists for decades. The corona, or the sun's outer atmosphere, reaches temperatures of several million degrees, far hotter than the surface itself. This puzzling difference is known as the coronal temperature anomaly, and it remains one of the most mysterious problems in solar physics. Intuitively, one would expect the outer layers of the sun to be cooler than the inner layers, but the opposite is true. The corona is dramatically hotter than the photosphere. Current theories suggest that the sun's magnetic fields may play a crucial role in heating the corona. These powerful fields extend from the surface into space and may be carrying energy upward. However, the exact mechanism by which this energy is transferred and how it results in such extreme temperatures is still not fully understood. Some scientists propose that alphane waves, ripples in the magnetic field, might be responsible. These waves could transport energy from the sun's interior into the corona, creating heat in ways we do not yet fully comprehend. Others suggest that magnetic reconnection, a process where magnetic field lines break and reconnect, releasing enormous amounts of energy, could also be contributing to the corona's intense heat. Despite decades of observation and research, the precise cause of the corona's extreme temperature continues to elude scientists. What makes this mystery even more significant is its potential impact. Understanding how the sun's corona works could improve our ability to predict solar storms, which can interfere with satellite communications, GPS systems, and power grids here on Earth. The cosmological lithium problem. Across the vast reaches of the universe lies a puzzle that has baffled scientists for decades: the cosmological lithium problem. It is a mystery woven into the fabric of the stars, raising an unsettling question. Where did all the lithium go? Lithium, a light element, was one of the first elements to form after the Big Bang. During a period known as Big Bang nucleosynthesis, the conditions of the early universe were just right for the creation of the first elements: hydrogen, helium, and lithium. These elements were produced in the hot, dense environment shortly after the universe began. However, astronomers and physicists have made a surprising discovery. When they examine the current amount of lithium in the universe, especially in ancient stars and galaxies, they find far less than predicted. According to the standard model of cosmology, the early universe should have produced significantly more lithium than what we observe today. The mystery is not that lithium is rare, but rather that there is a significant discrepancy between the theoretical predictions and actual observations. This gap is particularly evident in some of the oldest stars, which formed during the early stages of the universe. So what happened to the missing lithium? Some scientists propose that stellar processes, such as the fusion of elements inside stars, may be destroying lithium over time. However, this theory does not fully account for the large deficit of lithium observed in ancient stars. Other theories suggest that our current understanding of the early universe may be incomplete. Could there be unknown processes or hidden factors at play that reduce the amount of lithium that formed? Or is the solution buried in an overlooked aspect of astrophysics, waiting to be discovered? The cosmological lithium problem challenges our understanding of the universe's first moments. It urges scientists to revisit and refine their models of how the first elements were created. As we continue to search for answers, one thing remains clear: the universe still holds profound mysteries, ones that even our most advanced theories have yet to unravel. Mystery of the Titius-Bode law. A mysterious pattern was discovered in the distances between the planets in our solar system, so precise and consistent that it seemed too perfect to be random. This intriguing pattern became known as the Titius-Bode law, and for centuries, it has captivated scientists by offering an almost uncanny glimpse into the structure and organization of our cosmic neighborhood. The law itself is surprisingly simple. It suggests that the distances of the planets from the Sun follow a predictable mathematical sequence. Starting with Mercury, the planets appear to be spaced at regular intervals when measured using a specific formula. For example, Earth is located 1 astronomical unit, AU, from the Sun, while Mars is about $1.50 away. This spacing continues in a pattern that aligns closely with the predictions made by the Titius-Bode formula. This pattern was so accurate that it even seemed to predict the locations of planets not yet discovered. For a long time, the law appeared to work remarkably well for the known planets: Mercury, Venus, Earth, Mars, Jupiter, and even Saturn. But then came a puzzling exception: Uranus. According to the law, Uranus should have been at a different distance from the Sun than it actually is. Its location broke the pattern. Even more intriguing is the law's prediction of a celestial body between Mars and Jupiter. When astronomers looked in that region, they didn't find a planet, but they did discover the asteroid belt, a band of rocky debris orbiting the Sun exactly where the law had suggested something should be. These findings made the Titius-Bode law seem almost too accurate to be mere coincidence. Yet, the inconsistencies, like Uranus's unexpected position and the absence of any new planets at other predicted locations, have cast doubt on its reliability. So the mystery remains: is the Titius-Bode law just a numerical curiosity, a quirk of mathematical chance? Or could it point to a deeper, hidden principle governing the formation of planetary systems, one we have yet to understand? As we continue to explore the cosmos, the enigma of the Titius-Bode law lingers, leaving us with the eerie feeling that the universe might be revealing its secrets in ways we are only beginning to grasp. Fermi bubbles. To comprehend Fermi bubbles, we must journey into the heart of the Milky Way, where a strange and awe-inspiring phenomenon stretches across the center of our galaxy. These mysterious structures, known as Fermi bubbles, are vast, glowing regions filled with high-energy gas that have baffled astronomers since their discovery in 2010. Fermi bubbles are enormous, symmetrical formations of energy that extend roughly 25,000 light-years both above and below the galactic plane. They were first detected using data from NASA's Fermi Gamma Ray Space Telescope, which is designed to capture gamma rays, the highest energy form of radiation. The bubbles emit an intense glow in gamma rays, making them stand out against the backdrop of space. What makes Fermi bubbles truly mysterious is the question of their origin. Their size and power suggest that a massive, unknown event, or series of events, occurred in the Milky Way's core. One leading theory is that these bubbles were formed by energetic outflows from the supermassive black hole located at the center of our galaxy. As matter falls into the black hole, it may occasionally release powerful jets of energy, potentially inflating these massive lobes of gas. However, the timing and scale of such an event raise further questions. How could such a tremendous eruption extend so far from the galactic center? And why haven't we observed similar structures in other galaxies? Another intriguing theory proposes that the Fermi bubbles may be the result of something even more enigmatic: dark matter interactions. Dark matter is an invisible substance that makes up most of the universe's mass, yet remains poorly understood. Some researchers believe that unknown interactions involving dark matter could have contributed to the formation of these bubbles. Despite years of study, the Fermi bubbles continue to captivate scientists. Their haunting glow hints at powerful, hidden forces operating at the heart of our galaxy. And the true origin of these bubbles remains one of astronomy's most compelling unsolved mysteries. Could they be a sign of processes that challenge everything we know about the universe? For now, the answers remain just out of reach, inviting more exploration and more questions than ever before. The ghostly ring of dark matter. In the vast stretches of space, strange and unexplained phenomena continue to puzzle scientists. One of the most eerie and intriguing discoveries is the ghostly ring of dark matter. It may sound like something from a science fiction novel, but it is a real mystery grounded in modern physics. Dark matter is an invisible substance that makes up about 85% of the universe's total mass. It neither emits light nor energy, which is why it cannot be directly observed. We only know it exists because of its gravitational effects on visible matter. Recently, scientists made a startling discovery: an unusual ring-shaped structure that appears to be made of dark matter. This structure was found surrounding galaxies, and its properties are unlike anything previously observed. The ring seems to float independently, casting a gravitational influence despite being completely invisible. What makes this even more surprising is that the dark matter rings do not align with any existing theories of cosmic structure. They are too large, too well-formed, and too unusual to fit within the expected models of galaxy formation. Even more mysterious is the fact that these rings do not exhibit the typical characteristics of galaxy clusters or other known formations in the universe. Instead, they seem to suggest an unknown interaction involving dark matter, possibly originating from events that occurred during the earliest moments after the Big Bang. Could these ghostly dark matter rings be remnants of some ancient cosmic event? Or might they serve as a vital clue to uncovering the true nature of dark matter itself? Their discovery raises profound and unsettling questions about how dark matter behaves on the grandest scales. Is it possible that this invisible force is far more complex and organized than we ever imagined? For now, the ghostly ring of dark matter remains an unsolved enigma, one that might one day unlock deeper insights into the very fabric of the universe. Strange matter contagion hypothesis. Imagine a substance so bizarre and powerful that, if it were to come into contact with ordinary matter, it could transform everything it touches into a completely different kind of material. This is the chilling premise behind the strange matter contagion hypothesis, one of the most unsettling ideas in modern physics. Strange matter is a theoretical form of matter composed of strange quarks, particles that are typically found only under extreme conditions, such as inside neutron stars or during high-energy particle collisions. Unlike ordinary matter, which is made up of protons, neutrons, and electrons, strange matter is believed to be far more stable under immense pressure. It could potentially form a material that is significantly denser and more stable than anything naturally occurring on Earth. The true intrigue lies in the contagion hypothesis. This theory proposes that if strange matter were somehow created or discovered outside of these extreme environments, perhaps in a laboratory experiment or through a high-energy collision, it could begin to spread uncontrollably. In theory, it would convert any ordinary matter it encounters into more strange matter, much like a chain reaction. Once started, this process might continue indefinitely, consuming everything in its path. The result? The entire planet, or even the entire universe, could be transformed into this unfamiliar and alien form of matter. What makes this idea so disturbing is that we don't yet know whether strange matter actually exists, let alone whether it could spread in the way this hypothesis suggests. However, the mere possibility of such a transformation raises serious questions about the safety of high-energy physics experiments and the underlying stability of our universe. The strange matter contagion hypothesis is not just a scientific curiosity. It's a sobering reminder that the universe still holds mysteries that could challenge everything we think we know about matter, energy, and the laws of physics. While researchers continue to explore these questions, the potential threat posed by strange matter remains an eerie and fascinating possibility, lurking at the edges of human understanding. The vacuum catastrophe. The universe is often envisioned as a vast, empty expanse, filled only with a mysterious energy field known as the vacuum. This nothingness of space has long been accepted as the backdrop of all cosmic phenomena. However, what if this vacuum is not as empty as we once believed? What if it is on the brink of a cataclysmic shift, one that could alter everything we know? This is the enigma at the heart of the vacuum catastrophe. In physics, the vacuum is not truly empty. It contains a form of energy known as vacuum energy, which arises from the fluctuations of quantum fields. These fluctuations can cause tiny particles to appear and disappear in a continuous cycle. However, there is a major issue. When scientists attempt to calculate the amount of energy that should exist in the vacuum, they arrive at a number that is trillions of times larger than the actual energy we observe in the universe. This discrepancy is called the vacuum catastrophe. The mystery deepens when we consider the consequences of such a vast energy difference. Theoretically, if the vacuum energy were as high as predicted, it could cause the universe to collapse in on itself, essentially bringing an end to everything. The fact that this catastrophic event has not yet occurred is a source of confusion. How does the universe manage to avoid this grim fate? Some physicists propose that the vacuum could be in a metastable state, like a ball resting precariously at the top of a hill, poised to roll into a lower energy state. If this transition occurs, it could trigger a chain reaction that would fundamentally alter the structure of space-time, resulting in the destruction of everything as we know it. Yet, for now, this ticking time bomb remains stable. The vacuum catastrophe challenges our understanding of the universe's stability. How much do we truly understand about the fabric of reality? Could the very nature of nothingness hold the key to unlocking the universe's most profound secrets? These questions remain unanswered, leaving us to wonder just how fragile our reality might be. This is the riddle of zero-point energy. Zero-point energy exploitation. Imagine tapping into an energy source that's all around us, yet invisible, an endless, untapped reservoir of power capable of fueling the future of civilization. This is the promise of zero-point energy, a mysterious phenomenon existing at the quantum level of the universe. However, while scientists have speculated about its potential for decades, the central question remains: can we actually exploit it? Zero-point energy refers to the energy present in a vacuum, even when it appears empty. In quantum mechanics, particles are constantly fluctuating, popping in and out of existence, even in a perfect vacuum. These fluctuations mean that space is never truly empty, but is instead filled with subtle quantum energy. In theory, this energy is limitless, existing throughout the entire universe. The mystery lies in whether we can access and harness this energy for practical use. If we could tap into zero-point energy, it might provide an unlimited and clean power source. Imagine a world where energy scarcity is a thing of the past, and power is drawn directly from the vacuum itself. But there is a challenge. While zero-point energy is theoretically real, no one has yet figured out how to access it, or even if it's possible to do so. Scientists and inventors have proposed various devices that could extract this energy, but so far, none have been successful. Some researchers believe the key might lie in understanding the fundamental physics that govern quantum fields and space-time. Could there be a way to manipulate these fields, bending them to release the hidden energy? The mystery of zero-point energy exploitation challenges our understanding of physics and holds the potential to unlock a new era of technological advancement. Yet, until we discover a method to tap into this elusive force, the promise of zero-point energy remains just out of reach, teasing us with the possibility of an energy revolution waiting to be uncovered. Anti-gravity effects in superconductors. In the realm of physics, few phenomena are as fascinating and mysterious as the potential for anti-gravity. Imagine a material that, under the right conditions, could seemingly defy gravity, floating above the ground as if suspended by an invisible force. This is the intriguing possibility hinted at by the anti-gravity effects observed in superconductors. Superconductors are materials that, when cooled to extremely low temperatures, lose all electrical resistance. This allows electricity to flow through them without any energy loss. However, beyond their remarkable ability to conduct electricity perfectly, superconductors possess another strange, almost magical property. They can repel magnetic fields. This phenomenon is known as the Meissner effect. It plays a crucial role in how the anti-gravity-like behavior of superconductors might function. The Meissner effect causes a superconductor to expel magnetic fields from its interior, which can result in a levitation effect. When a superconductor is placed in a magnetic field, it pushes back against that field, creating the illusion of floating, an effect that resembles anti-gravity. Despite the fact that scientists have observed this levitation for decades, the underlying mechanisms remain poorly understood. Why do superconductors behave this way? Could this levitating effect be harnessed for practical applications such as transportation or advanced technology? Some researchers have speculated that these anti-gravity effects could even be used to develop gravitational shielding, a theoretical technology that might one day reduce or even eliminate the effects of gravity. If realized, such a breakthrough could revolutionize how we approach everything from space travel to energy use. Yet, despite significant advancements in superconductor research, no one has fully understood how these materials interact with gravity in a way that allows them to counteract it. The mystery of anti-gravity in superconductors continues to tantalize scientists and engineers alike, suggesting a future where we might one day manipulate gravity itself. From levitating vehicles to futuristic propulsion systems, the possibilities are vast. But for now, the exact nature of this strange phenomenon remains one of the greatest unsolved puzzles in modern physics. Could this be the first step toward a revolutionary new frontier of technology? Or is the true nature of anti-gravity still just beyond our grasp? The cold fusion phenomenon. Fleischmann and Pons made a groundbreaking announcement that sent shockwaves through the scientific community. They claimed to have achieved cold fusion. This process, which involves nuclear fusion, the same reaction that powers the sun, was said to occur at room temperature. If true, cold fusion had the potential to revolutionize the world by providing a limitless, clean, and sustainable source of energy. Under typical conditions, nuclear fusion requires extremely high temperatures and pressures, millions of degrees, to force hydrogen nuclei to fuse and form helium, releasing vast amounts of energy. Fleischmann and Pons' claim, however, suggested that this reaction could take place under much milder conditions, something previously unheard of in nuclear physics. Despite the excitement their announcement generated, the scientific community soon ran into problems. Numerous researchers attempted to replicate their results, but most efforts failed. These failures led to widespread skepticism, and many in the mainstream scientific world dismissed cold fusion as either an experimental error or a misinterpretation of data. Yet, the story doesn't end there. A small group of researchers has continued to explore the concept, occasionally reporting strange energy anomalies and unexplained experimental results. These findings, though inconsistent, keep the mystery of cold fusion alive. If cold fusion were proven to be real, it could offer a cheap, abundant, and non-polluting energy source, a perfect solution to the global energy crisis. However, the inability to consistently reproduce the phenomenon has left its legitimacy in doubt. Is cold fusion a real but elusive scientific breakthrough, or is it merely a myth that has yet to be debunked? The cold fusion phenomenon remains one of the most intriguing enigmas in modern science. It lingers as a tantalizing possibility, one that could fundamentally transform our understanding of energy production. Until the mystery is solved, it continues to challenge and inspire scientists to explore the uncharted realms of physics. The sonoluminescence paradox. In laboratory settings, something astonishing occurs when sound waves are amplified to extreme levels. Tiny gas bubbles, no larger than a speck of dust, suddenly emit bursts of light. This fascinating phenomenon is known as sonoluminescence, and it has perplexed scientists since its discovery decades ago. The central mystery lies in how a simple gas bubble, vibrating under the influence of sound waves, can produce such an intense flash of light. When sound waves strike a gas bubble submerged in liquid, they cause the bubble to rapidly collapse and compress. During this dramatic implosion, the bubble emits a brief, brilliant flash of light, almost as if a miniature star had flickered in a darkened room. This is where the paradox begins. How can such a small bubble, with no apparent energy source, generate light so intense that some estimates suggest the temperatures inside the collapsing bubble may exceed those found on the surface of the sun? The bubble is far too small to hold any conventional energy source, such as electricity or heat, that might explain this luminous burst. The paradox grows even deeper when considering the laws of energy conservation. Typically, light is produced from identifiable sources of energy, like chemical reactions, combustion, or electrical currents. Yet in sonoluminescence, the bubble seems to spontaneously convert sound energy, merely a mechanical pressure wave, into visible light. How can sound, a form of pressure, transform into light and heat without violating the established laws of physics? Despite decades of research, the precise mechanism behind sonoluminescence remains uncertain. Some researchers believe quantum mechanics may be involved, while others point to the incredibly complex dynamics of the collapsing bubble as the key. Sonoluminescence is more than just a fascinating laboratory curiosity. It represents a profound mystery that challenges our understanding of sound, energy, and light. It forces us to reconsider what is possible in the tiniest corners of the physical world. As the search for answers continues, This phenomenon remains one of the most intriguing puzzles in modern physics, inviting us to explore what secrets the universe might be hiding inside the smallest of bubbles. Emission of X-rays from comets. Comets are among the most mysterious objects in our solar system, traveling silently through the vast emptiness of space with their long, dusty tails trailing behind them like celestial ribbons. For a long time, scientists have known that comets are composed primarily of ice, dust, and gases. However, a puzzling phenomenon has challenged this basic understanding. Under certain conditions, comets emit X-rays. X-rays are high-energy radiation typically associated with extremely hot or energetic environments, such as the sun, neutron stars, or black holes. It seems counterintuitive that icy bodies from the distant reaches of the solar system could be sources of such powerful radiation. This surprising discovery was first made in the 1990s, when scientists observed unexpected X-ray emissions from comet Hyakutake. The same phenomenon was later confirmed in comet Hale-Bopp. These comets, like others, release gas and dust as their icy cores begin to vaporize while approaching the sun, forming the bright and expansive tails visible from Earth. Still, no one anticipated that this process would also produce X-rays. So where are these X-rays coming from? The mystery deepens as researchers explore the possible mechanisms behind this radiation. One leading theory suggests that X-rays are generated when solar wind, streams of charged particles emitted by the sun, collide with the gas in a comet's coma, the cloud of gas and dust that surrounds the nucleus. These interactions may create energetic reactions that result in X-ray emissions. However, this theory doesn't fully account for the variations observed in the intensity of X-rays. Sometimes the emissions are stronger. Other times, they are weaker, often depending on the comet's position relative to the sun. This inconsistency suggests that there may be additional, unknown factors at play, perhaps a previously unidentified type of interaction or force. The mystery of X-ray emissions from comets is a powerful reminder of how much we still have to learn about the universe. These ancient travelers from the outer solar system continue to surprise scientists, revealing hidden complexities that challenge our understanding of both comets and the dynamic forces that shape our cosmic neighborhood. Long-delayed echoes of radio signals. Imagine sending out a radio signal, but instead of hearing it just once, you hear it again and again, each time delayed by several seconds. It's as if the signal is bouncing off something far away and returning long after the original transmission. This strange and fascinating occurrence is known as the phenomenon of long-delayed echoes, LDs, a mystery that has puzzled scientists for decades. The first reports of long-delayed echoes date back to the 1920s, when radio operators noticed that signals sent from Earth didn't always travel in a direct path through the atmosphere. Instead, some signals would unexpectedly bounce back after a significant delay, sometimes lasting several seconds or even minutes. These echoes were unlike any typical reflections caused by nearby objects like buildings or mountains. They seemed to originate from high in the atmosphere, or perhaps even from space. One widely accepted theory attributes these echoes to the ionosphere, a layer of Earth's upper atmosphere that can reflect certain radio frequencies. Under normal conditions, the ionosphere helps transmit radio signals over long distances. However, when disturbed, this layer could potentially reflect radio waves in unpredictable ways, causing them to return to the source after a long delay. Despite this theory, not all aspects of the phenomenon are fully explained. Some of the echoes show delays that are longer and more erratic than what the ionosphere alone can account for. This has led some scientists to propose more unusual possibilities. Could unknown interactions within the atmosphere be at play? Are there still undiscovered layers or structures high above the Earth that reflect signals in ways we don't yet understand? There's even speculation that these echoes might come from mysterious regions of space or be influenced by forces we have yet to identify. While the true cause of long-delayed echoes remains elusive, the phenomenon continues to intrigue researchers and spark new questions. In the end, long-delayed echoes serve as a reminder that the natural world, and the space just above our heads, may hold secrets that science has yet to fully uncover. The echoes whisper of an unseen complexity in our universe, hinting that there's still so much more to learn. Fast radio burst patterns. In the vastness of space, there exists a mysterious and haunting signal known as a fast radio burst, or FRB. These are high-energy bursts of radio waves that last for only a few milliseconds. Yet, in that brief moment, they release more energy than our entire sun emits in an entire day. What makes FRBs especially intriguing is that we still don't know what causes them. Adding to the mystery is the discovery of strange patterns in their occurrence. Since their first discovery in 2007, fast radio bursts have baffled scientists. These bursts appear to originate from far beyond our galaxy, but their exact source remains unknown. Despite their incredibly short duration, often just a fraction of a second, the amount of energy they produce is staggering. It's as if the universe is sending out a powerful cosmic flash. But from where? And why? The mystery deepens when scientists analyze the patterns in these bursts. Some FRBs seem to follow a regular schedule, repeating at predictable intervals. Others travel through space in ways that suggest they might be influenced by some unknown structure or force. This repetitive behavior suggests that FRBs are not random events, but may be connected to specific cosmic phenomena. Researchers speculate that these signals could be tied to extreme magnetic fields or exotic celestial objects, such as neutron stars or black holes. Some have even proposed the idea that FRBs might be signals from alien civilizations, though that remains purely speculative. The more widely accepted explanation involves intense astrophysical events. Still, the exact cause of FRBs remains one of the most captivating mysteries in modern astrophysics. Every new FRB discovery adds to the enigma, pushing scientists to reconsider our understanding of space and energy. Are we witnessing the echoes of distant cosmic events? Or could there be a hidden force in the universe that we have yet to uncover? For now, the answers remain elusive, but the search continues, drawing us deeper into the unknown. Neutron star glitches. At the heart of space lie objects so dense and mysterious that their very existence challenges the limits of human understanding. These are neutron stars, the remnants of massive stars that have exploded in cataclysmic supernovae. Among the strangest and most fascinating objects in the universe, neutron stars are incredibly compact, containing more mass than our sun within a sphere only a few kilometers in diameter. Yet, despite decades of study, neutron stars continue to puzzle scientists. One of their most baffling behaviors is the sudden and unexplained phenomenon known as glitches. These glitches are abrupt changes in the star's rotation that momentarily disrupt its otherwise predictable behavior. Neutron stars spin at astonishing speeds, often hundreds of times per second, and emit beams of electromagnetic radiation. When these beams sweep across Earth, we detect them as regular pulses, leading to the term pulsars. These pulses usually follow a steady, clock-like rhythm. However, from time to time, something unusual occurs. The pulse timing suddenly shifts or becomes irregular, as if the star itself has momentarily stumbled. These glitches can vary in intensity. Some cause only a slight deviation in the timing of the pulses, while others lead to more dramatic breaks in the star's regular pattern. What causes these sudden disruptions remains a profound mystery. Several theories attempt to explain the origin of neutron star glitches. Some scientists suggest that they may be caused by internal shifts in the star's dense, superheated core. Others believe the star's crust, under immense pressure, may crack or rearrange itself, triggering the glitch. There are also hypotheses involving the neutron star's powerful magnetic fields, which could play a role in disrupting its rotation. However, the most intriguing and unsettling possibility is that these glitches point to phenomena we do not yet understand. They might be the result of exotic quantum effects or entirely new laws of physics waiting to be discovered. Could it be that neutron stars are revealing behaviors that challenge our current understanding of matter, energy, and even space-time itself? The phenomenon of neutron star glitches remains one of the great cosmic mysteries. Each new glitch provides scientists with a fleeting glimpse into the powerful and hidden forces at play within the universe's most extreme environments. And with every unexplained pulse, the mystery deepens, drawing us closer to the truth behind these strange celestial anomalies. Strange pulsar signals. Deep in the vastness of space, there exist stars that behave in truly extraordinary ways. Among them are pulsars, rapidly spinning neutron stars that emit regular pulses of energy, like cosmic beacons flashing across the galaxy. These signals are typically steady and predictable, forming a rhythmic pattern that scientists have studied and understood for decades. However, every now and then, something unusual occurs, pulsar signals that defy all known explanation. The mystery of these strange pulsar signals began with a remarkable discovery in 2018. Researchers observed a pulsar emitting irregular, seemingly random bursts of energy, something unlike anything previously recorded. Instead of the typical steady, lighthouse-like pulses synchronized with the star's rotation, this pulsar produced erratic signals marked by sudden gaps, bursts, and shifts in frequency. These anomalies suggested that something was interfering with the pulsar's regular behavior. This puzzling phenomenon led scientists to speculate about possible causes. One idea was that the pulsar might be interacting with something in its immediate environment, perhaps a companion star or a disturbance in the surrounding magnetic fields. Another theory proposed that internal processes within the pulsar itself, such as changes in its crust under extreme pressure, could be responsible for the altered signal patterns. But the mystery doesn't stop there. Some scientists believe these strange signals might point to something far more elusive. Could they be evidence of unknown cosmic phenomena or even exotic physics? There has even been speculation that the irregular bursts could result from interactions with dark matter or quantum fields behaving in ways we've never before observed. These unusual pulsar signals continue to baffle astronomers. Yet with every new anomaly, we inch closer to understanding the hidden forces shaping these enigmatic stars. The question remains, what is truly behind these unexpected, eerie signals? And could they be leading us toward a deeper, undiscovered layer of the universe? Ultra-high-energy neutrinos. Ultra-high-energy neutrinos are some of the most mysterious and fascinating particles in the universe. These tiny, elusive particles can pass through our planet, and even our own bodies, without leaving a trace. Known simply as neutrinos, they rarely interact with matter, making them extremely difficult to detect. However, there's a specific kind of neutrino that has scientists especially intrigued: ultra-high-energy, UHE neutrinos. These neutrinos are not only incredibly rare, but they also carry energy levels far greater than those typically found in cosmic radiation. They originate from the depths of space, and when they are detected on Earth, they offer a rare and valuable glimpse into the most energetic and mysterious events in the cosmos. The catch? We don't yet know exactly where they come from. UHE neutrinos have been detected by observatories like the Ice Cube Neutrino Observatory, located at the South Pole. This facility uses thousands of sensors buried deep in Antarctic ice to detect the faint signals produced when neutrinos interact with the ice. By analyzing these interactions, scientists can attempt to trace the path of these particles back to their origins. Still, the true sources of UHE neutrinos remain a mystery. Some scientists believe they could be coming from supermassive black holes at the centers of distant galaxies. Others point to gamma-ray bursts, the most powerful explosions in the known universe, as potential sources. Yet, no definitive origin has been confirmed. What makes UHE neutrinos so captivating is how they challenge our current understanding of physics. How do these particles achieve such extreme energies? How can they travel across vast cosmic distances without losing that energy? Some researchers even speculate that UHE neutrinos might be linked to dark matter or other unknown cosmic phenomena, forces that remain undiscovered. The mystery of ultra-high-energy neutrinos pushes the boundaries of what we know about the universe. Solving it could unlock entirely new insights into the structure of space, time, and the fundamental forces of nature. In fact, their existence even relates to the GZK limit, a theoretical boundary on the energy of cosmic rays, which UHE neutrinos seem to defy. In short, ultra-high-energy neutrinos represent one of the most exciting frontiers in modern astrophysics, an invitation to explore the unknown and uncover new chapters in our understanding of the universe. The GZK limit and the mystery of cosmic rays. In the vastness of space, high-energy particles known as cosmic rays race through the universe, traveling at nearly the speed of light. These particles are among the most energetic phenomena we've ever discovered. Yet, they appear to originate from places so distant, it's as though they're arriving from another time. But here's where the mystery begins. Some of the most powerful cosmic rays seem to break a fundamental rule of physics. According to our current understanding, they shouldn't be able to reach us at all. This puzzling phenomenon is known as the GZK limit, named after the scientists Grison, Zatsepin, and Kuzmin, who first proposed it. The GZK limit predicts that the highest energy cosmic rays cannot travel more than about 100 million light-years without losing a significant amount of their energy. This is because, along their journey, these rays constantly collide with particles in the cosmic microwave background, CMB, a faint glow of radiation left over from the Big Bang. These collisions are expected to drain their energy, preventing them from ever making it to Earth. Yet, despite this well-established prediction, astronomers have detected ultra-high-energy cosmic rays arriving from galaxies that lie well beyond this limit. These particles somehow retain far more energy than they should be capable of maintaining over such immense distances. This raises a critical question. How are these cosmic rays reaching us? Some scientists speculate that these rays may actually be coming from closer sources, such as active galaxies or supermassive black holes that haven't yet been identified. Others propose more radical ideas, that unknown forces or exotic particles, possibly linked to dark matter, could be influencing their journey. Could these cosmic messengers be hinting at new, unexplored physics? The mystery of the GZK limit challenges our current understanding of the cosmos. It suggests that the universe might be far stranger and more complex than we ever imagined. These cosmic rays, racing through the fabric of space-time, may carry secrets that could transform how we view the universe itself. As scientists continue to investigate, the mystery only deepens. Theories about hyperspace jumps and other speculative ideas begin to surface, each one offering a glimpse into the possibility that the universe holds more surprises than we've yet dreamed. Hyperspace jump theories. The concept of hyperspace travel is the idea of being able to cross vast distances of space in the blink of an eye. Imagine a way to jump from one point in the universe to another, bypassing the long and slow journey through the cosmos. This concept, which seems straight out of science fiction, has been a mystery that has captivated physicists for decades. The idea of hyperspace travel stems from the theory that, under certain conditions, the fabric of space-time could be manipulated in such a way as to allow for faster-than-light travel. Instead of moving through space in the traditional sense, a spacecraft could potentially enter a higher-dimensional space, a kind of shortcut through the universe that bypasses the enormous distances between objects. One of the most famous theories associated with hyperspace jumps involves wormholes, hypothetical passages through space-time that could connect distant regions of the universe. Picture them as tunnels in the fabric of space, where one end could be near Earth and the other in a distant galaxy. If wormholes exist, they might allow for rapid travel between far-flung locations. However, there's a significant problem. We've never observed a wormhole. Even if they exist, scientists still don't know how to keep one open or stable enough for practical use. Another theory for hyperspace travel involves manipulating space-time itself using advanced technology, such as warp drives. In theory, a warp drive could bend space in front of a spacecraft, creating a bubble that moves faster than light without actually violating the laws of physics. But, as with the wormhole theory, this idea faces immense challenges, particularly because the energy required to achieve such a feat would be astronomical. The mystery of hyperspace travel leads to deeper questions about the nature of space and time. Could there be hidden dimensions or forces at play that we have yet to discover? Hyperspace travel challenges our current understanding of the universe, leaving us with a tantalizing question. Is the key to faster-than-light travel already embedded within the very fabric of reality, just waiting for us to unlock it? Simulation hypothesis backed by physics. What if everything you see, hear, and experience is not actually real, but part of a simulation? The idea that we may be living in a computer-generated simulation has gained increasing attention, particularly with advancements in technology and physics. Some theorists suggest that the universe itself could be a highly sophisticated simulation created by an advanced civilization. While it sounds like science fiction, proponents argue that certain aspects of physics, particularly the nature of quantum mechanics, could support this hypothesis. Could our reality be a program running on a super-advanced computer? It's a mind-boggling thought, but it raises profound questions about the nature of existence and the limits of human understanding. The simulation hypothesis, supported by concepts in physics, suggests that our experience of reality may be nothing more than an incredibly advanced simulation, similar to a video game, yet so sophisticated that it feels entirely real. This unsettling possibility forms the essence of the simulation hypothesis, which has moved beyond the realm of science fiction into serious scientific discourse, bolstered by some surprising aspects of physics. The core idea is simple. Perhaps the universe itself is a simulation created by a highly advanced civilization. This concept is analogous to how we simulate virtual worlds in video games, but on a far grander, cosmic scale. Even more intriguing is the suggestion that some aspects of physics may actually support this theory. One of the key points lies in the strange nature of quantum mechanics, where particles often behave in ways that defy traditional understanding. For instance, particles can exist in multiple states simultaneously until observed, and the very act of measurement can alter their behavior. Some theorists propose that these bizarre phenomena could be indicative of an underlying code or set of rules governing a simulated reality. After all, in a computer simulation, entities and phenomena only exist when they are observed or interacted with. Could these strange quantum behaviors be evidence of a simulated reality? This is a question that many have pondered. Another compelling argument comes from the limits of computing power. As technology advances, humans are creating increasingly sophisticated simulations that present virtual worlds indistinguishable from reality. Some theorists argue that if future civilizations continue to advance technologically, they might one day possess the computational power needed to simulate entire universes. If they can create such simulations, why couldn't we be living in one? Although there is no definitive evidence to prove the simulation hypothesis, the idea that our reality might be a simulation challenges our fundamental understanding of existence. If the universe is indeed a construct, one that can be manipulated or programmed, It forces us to grapple with one of philosophy's most enduring questions. What is the true nature of reality? And if we are living in a simulation, what exists beyond the boundaries of our perceived world? One further concept that ties into this idea is retrocausality, the notion that events can be influenced by future events, which would add another layer of complexity to the idea that our universe could be a simulated construct. Retrocausality refers to the concept that effects can precede their causes, essentially suggesting that the future can influence the past. This idea may sound like something out of science fiction, but it has intrigued physicists and philosophers for many years. In the realm of quantum mechanics, time behaves in ways that often defy our everyday understanding. In our normal lives, we're accustomed to causes leading to effects in a clear, logical order. One event happens, and then it causes another to follow afterward. However, at the quantum level, particles behave quite differently. They can exist in multiple states at once, and what occurs next might depend on how we observe them. This is where retrocausality comes into play. Imagine if the behavior of particles in the present could be influenced by events that happen in the future. What if, under certain conditions, the future actually causes something to occur in the past? This would completely challenge our traditional understanding of time. Some theories suggest that retrocausality might explain strange phenomena, such as quantum entanglement, where two particles can instantly affect each other, no matter the distance between them. Typically, we think of events unfolding in a linear direction, from past to present to future. But retrocausality suggests that the future could, in some mysterious way, reach back and alter events that have already taken place. The implications of this idea are mind-boggling. Could time travel be possible, not in the way we traditionally imagine, but through future events influencing the past? And if retrocausality is true, does this mean that time itself is not as linear and fixed as we once believed? For now, the mystery of retrocausality remains unsolved. But with each new discovery in quantum physics, we move one step closer to answering this unsettling question. Is time really just a one-way street? Or could it be much more fluid than we ever imagined? The possibility of closed time-like curves further adds to the intrigue surrounding this topic.